The stars no longer hide in myth, they emerge in silence, distant and dark, yet full of consequence. Across the black velvet sky, not all light comforts. Some stars vanish, some twist space itself, and some remain unseen, detectable only by the havoc they unleash. Our understanding of the universe, for all its equations and theories, is still young, still vulnerable to awe. Somewhere, an object moves in the darkness, not shining, but devouring, not drifting, but warping reality. Its name, black hole, a phrase that once sounded fictional, now confirmed by images in abyss where matter falls, where time distorts, and where physics as we know it breaks down. It begins with a star, a massive one. When its nuclear fire runs out, gravity wins. The star collapses inward, not into a denser form of itself, but into a singularity, a point of infinite density, zero volume, around it. The event horizon marks a threshold from which no return is possible. Light cannot escape. Information cannot escape. What happens inside remains beyond comprehension. It is not just a physical phenomenon. It is a border between knowledge and the unknowable. And yet, we have seen its outline. In 2019, a ring of fire blurred into focus, an image carved by radio waves and stitched together by a planet-wide array of telescopes. The event, Horizon Telescope, gave humanity its first glimpse of the unseeable, the shadow of a supermassive black hole in M87, 55 million light-years away. The image was not sharp, but it was profound. For the first time, we stared into the mouth of gravitational collapse. But black holes are not distant myths, they are potentially closer than we'd like. Some wander. Rogue black holes drift invisibly through galaxies, their paths uncertain. Should one ever pass near our solar system, its pull could distort orbits, unsettle planets, even cast Earth into cold exile or toward fiery doom. The odds are low, but the possibility real. Still more violent are the bursts of light that seem to arrive from nowhere. In the Cold War's shadow, satellites designed to catch nuclear flashes instead captured something stranger: gamma-ray bursts. These were no tests. They were cosmic, brief eruptions, milliseconds to minutes long, that unleashed more energy than our sun will emit over 10 billion years. Some came from collapsing stars, others from the collision of neutron stars, corpses of stars smashing into each other in their death throes. If one of these bursts were aimed directly at Earth from within our galaxy, its effects would be swift and devastating. The ozone layer would disintegrate. Ultraviolet light would flood the surface. Plankton, plants, people all exposed to invisible death. Even oceans would offer little refuge. The last time this might have happened, some suspect the Ordovician extinction, 450 million years ago, was triggered by just such a burst. Nature's cosmic reset. Less comforting are the objects that remain after collapse, yet do not vanish. Neutron stars. Objects so dense that a teaspoon of their matter outweighs every skyscraper on Earth. The crust is solid, but beneath it, a sea of degenerate neutrons. A collapsed heart of a once living sun. Some spin hundreds of times per second, sweeping space with beams of radio waves, pulsars. Others twist magnetic fields into monstrous tension magnetars. When they crack, space itself shakes. In 2004, a magnetar 50,000 light-years away emitted a flash so intense that it briefly altered Earth's upper atmosphere. That is the power of a dying star's magnetic scream. And these remnants do not stay still. Some fly stellar bullets, speeding at over 1,000 kilometers per second. Most are far, safely distant. But the knowledge remains space harbors forces too ancient to reason with. There is more. Things we cannot see, but which shape the universe. Dark matter. It bends light. It anchors galaxies. It outweighs visible matter 5 to 1. But what is it? A particle of field. A fabric of some parallel physics. We don't know. We only know it is there. We see galaxies spinning faster than they should. Stars that cling to the edges of spirals like dancers defying momentum. Only the invisible mass of dark matter explains their motion. It does not shine, does not absorb, does not scatter light. It simply exists like gravity, like fate. Our Milky Way swims in a dark halo, unseen but binding. We owe our structure, even our formation, to it. And yet, dark matter might not be passive. Some theorize it could decay, collapse, trigger events more violent than any supernova. We build detectors deep underground, shielded from the noise of cosmic rays, hoping to catch a glimpse of this elusive substance. But so far, silence. If it touches us, it does so without trace. We live in a universe where what we see is not what we get. Only 5% of the cosmos is visible. The rest hides in shadow, in matter and energy that ignore our senses. But not our fate. The galaxies stretch out like a frozen dance, swirling spirals, gnarled ellipticals, warped irregulars, each a city of suns, each a whisper of ancient collisions. Seen through modern telescopes, they appear suspended, drifting in the void. But this stillness is an illusion. Galaxies move. They fall. They collide. The Milky Way itself is not isolated. It hurtles through space at 600 kilometers per second, drawn into a vast current of gravitational flow known as the Laniakea supercluster. Around it orbit smaller galaxies, the Magellanic Clouds, the Sagittarius Dwarf, and ahead, a collision waits. In 4 billion years, Andromeda and the Milky Way will meet, not crash, like stones, but merge like fog banks. Their stars will mostly pass through each other, but gravitational tides will distort, stretch, and finally bind them into a new, giant elliptical galaxy. Our sun may survive, Earth may not. This future was not always knowable. For centuries, nebula meant any fuzzy light in the sky. Through Galileo's telescope, some nebulae became stars. Others, like Andromeda, remained strange. Were they gas clouds or island universes, as some guessed? William Herschel, a musician turned astronomer, resolved many nebulae into clusters. He assumed interstellar space was transparent. Stars were like the sun, and their brightness revealed distance. Based on these, he concluded the Milky Way was a flat disk, and that we were near its center. But assumptions mislead. Dust clouds obscure light. Stars vary. The cosmos misbehaves. His son, John Herschel, carried the work forward, more cautiously, and as telescopes improved, so did skepticism. By the 19th century, 2 interpretations competed. One saw the nebulae as distant galaxies' other Milky Ways. The other saw them as forming solar systems, gas clouds coalescing into stars. One vision implied a many-island universe, vast and populous. The other, a singular local system, the one-island cosmos of Victorian confidence. William Huggins helped resolve the dispute. In 1864, he turned a spectroscope toward a planetary nebula in Draco. He expected to see a stellar spectrum, a continuous band broken by absorption lines. Instead, he saw bright emission lines gas. The nebula was not a star cluster. It was glowing vapor. This discovery collapsed centuries of speculation in a single night. The heavens, it turned out, were more diverse than imagined. But not all nebulae were gas. Others, like Andromeda, displayed spectra like stars continuous with absorption lines. These were not clouds, they were galaxies, whole star systems, swirling far beyond our own. The Great Debate of 1920 pitted 2 astronomers, Shapley and Curtis, against each other. Shapley argued for a massive Milky Way, containing all. Curtis countered the Milky Way was one among many galaxies. Their disagreement hinged on distance. Shapley overstated it. Curtis understated it. In the 1920s, Hubble used the 100-inch telescope at Mount Wilson to study Cepheid variable stars in Andromeda. These stars pulse in brightness with periods linked to their luminosity, a cosmic yardstick. Hubble's measurements revealed that Andromeda was over 2 million light-years away, far outside the Milky Way. It was a galaxy. The universe had opened, but Hubble saw more. As he examined more galaxies, he noticed a pattern the farther away they were. The more their light was redshifted, a Doppler effect. Galaxies were receding, all of them. Space itself seemed to stretch. This expansion wasn't explosion, it was metric. Not galaxies moving through space, but space expanding between galaxies. The universe was not static. It had a history. Einstein, who had once introduced a cosmological constant to hold the universe in eternal equilibrium, famously called it his greatest blunder. But it wasn't. Not entirely. In modern cosmology, the cosmological constant has returned as dark energy, an unseen force accelerating expansion. Dark energy, a phrase that names our ignorance. It comprises nearly 70% of the universe. It is not matter, not light, not dark matter. It is not even energy in the conventional sense. It is an intrinsic property of space, a pressure that drives galaxies apart faster and faster. We live in a universe whose dominant component we cannot see, measure directly, or fully describe. We observe its consequences. We know its percentage, but its essence escapes us. Still, we persist. We build observatories at high altitudes, below Antarctic ice, in deep mountain tunnels. We launch telescopes above the atmosphere, probing ancient starlight stretched by billions of years. We listen for neutrinos, capture cosmic rays, and sift through microwaves left over from the Big Bang. And in that afterglow, the cosmic microwave background, we find our earliest snapshot. A time when the universe was just 380,000 years old, dense and hot and full of plasma. As it cooled, photons decoupled, and light could finally move freely. That light still travels, cooled and stretched, whispering of a primordial time. There, encoded in slight temperature fluctuations, is the fingerprint of the infant universe, the seed patterns from which galaxies grew. These tiny irregularities, amplified by gravity, would become clusters, filaments, voids. Our universe is not uniform. It is clumpy, textured, hierarchical. Stars gather in galaxies. Galaxies cluster. Clusters assemble into superclusters, connected by filaments of dark matter, surrounding vast voids, a cosmic web fractal in pattern, immense in scale. And yet, with enough distance, it smooths. On the largest scales, the universe appears homogeneous, isotropic, every direction the same, every place equivalent. A paradox resolved in inflation, a theory proposing that, in the first sliver of a second after the Big Bang, space expanded faster than light, ironing out irregularities, stretching quantum fluctuations into cosmic structure. From subatomic jitter to galactic scaffolding, it is strange to think the stars above are ancient. Their light, a memory, their structure, shaped by events that occurred before atoms even existed. Time, in cosmology, is not linear. It is a telescope pointed backward. The deeper we look, the younger the light. The farther the distance, the closer we come to the origin. And yet, what lies ahead? The night the sky darkened and suddenly flared with new light. People felt that the heavens had awakened. That moment mirrored a revolution in our understanding of cosmic time and structure. When astronomers carefully measured the redshift of distant galaxies, they saw that the farther a galaxy lay, the faster it receded, evidence that space itself is expanding. That simple motion recast space from a static stage into a living actor, stretching and curving as the universe ages. With expansion came a beginning, an event, the Big Bang, that set all things in motion, matter and time alike. Tracing that origin led scientists to measure the faint afterglow of creation. A relic they call the cosmic microwave background, a pale whisper from when the universe was only a fraction of its current age. From that glow emerged the cosmic web, filaments of galaxies threaded across voids, the grand architecture of structure itself, the stars within those galaxies, born in swirling clouds of gas and dust, traced paths not just of gravity, but of meaning, tiny engines forging elements, lighting planets, life, and understanding. Yet new questions emerged faster than answers. What drives cosmic acceleration? How precise are those physical constants that shape stars, chemistry, life, and death? Shift gravity by a whisper, or tweak electron charge by a breath, and stars never form, or atoms never bind. The universe felt pre-configured not for randomness, but for possibility. A silent design without a designer. One idea crystallized in response to the anthropic principle. It doesn't imply purpose, only perspective. Of all possible universes, only those with the right conditions could support observers. We find ourselves in one such universe by necessity. It is tautological, yet not empty. This reasoning raises the question of what else exists. Might there be many universes? A multiverse, each with its own laws, its own histories, and maybe its own inhabitants. In some inflation models, quantum fluctuations cause separate regions of space to bud off into distinct universes, bubble universes with different physical constants. String theory suggests a landscape of as many as 10 to the power of 500 possible laws. In quantum physics, the superposition of all possibilities is literal. These ideas push our minds to the boundary between what we can test and what we can only imagine. Black holes, once theoretical oddities, now anchor tests of gravity, quantum mechanics, and information itself. Infalling matter carries information, but classical black holes erase any trace. Stephen Hawking showed that black holes emit radiation, slowly leaking mass. But if radiation is featureless, does the information vanish forever? This is the black hole information paradox, a crossroads between the certainty of quantum theory and the collapse of classical determinism. Some believe that information is stored in the event horizon, entangled in subtle ways with the hidden interior. Others propose that space-time itself emerges from patterns of quantum entanglement, that gravity is a thermodynamic consequence. If so, the black hole horizon is a place where particles, geometry, and information coalesce into one story. Cosmology balances under this tension. Ordinary matter atoms, molecules, dust makes up only 5% of the universe. The rest is dark 27% dark matter, and nearly 70% dark energy. Galaxies, including our Milky Way, float in massive halos of dark matter, a silent scaffolding revealing itself only through gravity. Dark energy accelerates everything outward, driving space into a future of isolation. Our cosmic model today has shape flat, expanding, seeded by inflation, structured hierarchically stars, galaxies, clusters, and evolving through lifetime stardom, supernova, black holes, entropy. It maps what we can observe, it omits what we cannot. But at the edges of this map lie puzzles. What is dark matter made of WIMPs or actions? Primordial black holes or undiscovered particles? Are we certain that dark energy is constant, or might it evolve, or even reverse future exploration underground labs, particle accelerators? Next-generation telescopes might reveal the substance of darkness, or hint at deeper symmetries yet unseen. The two great ideas, the anthropic principle and the multiverse, come from the same trembling frontier. Why these laws? Why this universe? If the multiverse is real, we may be just one observer among countless pocket universes, each with different physics. That idea shifts cosmology into philosophy, and philosophy back into science. Because even if other universes lie forever beyond observation, our models must account for the possibility they shape the questions we ask, the experiments we design, the telescopes we build. But we peer outward, not just in search of space, but in search of ourselves. We trace every atom of our bodies back to ancient supernovae. We are endings of long stellar chains. In searching for cosmic origins, we stumble upon our own. Consciousness, reflection, our awareness of time, these may be among the rarest products of the cosmos. In that sense, the universe's true aim may not be complexity, but comprehension. And so cosmology becomes a quiet story of orientation, not merely where and when we are, but how and why we think. To look outward is, in effect, to look inward, mirror to galaxy, neuron to network. That mirror reflects our own limits at the boundary of what is observable, describable, explainable. In a quiet chamber cooled to near absolute zero, a scientist adjusts a detector buried deep beneath the earth. It waits for a flicker, a collision so faint it might happen once in a year, or not at all. The target, dark matter, unseen but suspected, expected but never confirmed. The hope that this one invisible thread might unravel the nature of 95% of reality. Cosmology has long been about the visible stars, planets, nebulae, galaxies, but modern cosmology leans on the unseen. It maps absence as rigorously as presence. It begins to ask not just what the universe contains, but what it permits. The visible cosmos is structured, but why does that structure arise at all? Stars cluster, galaxies rotate, filaments stretch across voids. These patterns come not from matter alone, but from the early quantum fluctuations, microscopic randomness inflated to galactic scale. Tiny jitters in the vacuum, writ across light years. Without that randomness, there would be no galaxies, no planets, no observers. That lesson reappears across scales. The universe is not deterministic in a classical sense. It is probabilistic, governed by wave functions, not certainties. Even the vacuum is alive, roiling with potential. Virtual particles flicker into existence and vanish. This quantum nature is not confined to the microscopic. It shapes cosmology. Space, too, may not be fundamental. In some models, it emerges from quantum entanglement, from information networks, from something deeper than geometry. Just as temperature arises from the motion of atoms, space might arise from correlations between quantum states. What we call distance could be an illusion of connectivity. Time may also be emergent, or relational, or partial. In the block universe view, time is a dimension like space, every event already embedded in a static four-dimensional structure. Past, present, and future coexist, experienced differently by different observers. In loop quantum gravity, time arises from spin networks and their evolution. In other views, time is not real at all, a byproduct of entropy and memory. Entropy, the measure of disorder, gives time its arrow. We remember the past because entropy increases. Eggs break, ice melts, stars die, galaxies spread. The universe ages not because time flows, but because disorder grows. The second law of thermodynamics is the one arrow that never bends backward. As entropy climbs, the universe evolves. Stars burn out, galaxies thin, black holes evaporate. What remains, in trillions of years, is not silence, but equilibrium, a heat death where energy is uniform and nothing more can happen. No gradients, no structure, just particle haze in infinite night. But even this may not be final. Some theories suggest the vacuum is not stable. It could decay into a lower energy state, triggering a phase transition, a bubble of true vacuum expanding at light speed, unmaking everything. The end not by cold, but by transformation. Other models imagine rebirth, a big bounce where contraction replaces expansion, and a new universe emerges from the wreckage of the old. Or cyclic models, where the cosmos undergoes endless epochs, each one birthing space, time, matter, and then dissolving again. These universes have memory, rhythm, cadence. The end is never the end. If space-time itself is emergent, then what lies beneath may be timeless and placeless, a quantum substrate, a mathematical structure, a code. Some theorists see reality as computation, a cosmic quantum computer evolving states. Others imagine networks, nodes, and links, like neurons, but more fundamental in coding the shape of existence. This vision blurs physics with metaphysics. It invites us to ask, is the universe something, or is it the pattern that something makes? Is it substance, or relation? In this light, the question of consciousness reappears. If the universe is informational, and observers are pattern detectors, then consciousness may be the universe reflecting on its own dynamics. The philosopher Thomas Nagel once wondered what it's like to be a bat, but cosmology might ask what it's like to be a galaxy, or a quantum field, or a self-aware fragment of the universe able to model the whole. Our experience of time, of motion, of becoming may be a local echo of deeper dynamics. In some theories, consciousness collapses the wave function. In others, all possibilities exist, and consciousness simply follows a path. Still others suggest consciousness is a feature of complexity, not fundamental, but emergent, like weather or language. And yet, here we are embedded in time, curious and limited, glimpsing the infinite through finite means. Our models grow more precise, more abstract, more unified, but they are not ends. They are bridges. Theories of everything aim not to replace mystery, but to frame it, to convert unknowns into structured not knowing. In this work, cosmology becomes both a science and a mirror. It studies stars and galaxies, but it reflects meaning, place, and awareness. It shows us not only how far we are from the center, but how far we've come from not knowing at all. The edge of understanding is not a void. It is a contour ever shifting, shaped by questions we dare to ask. A neutrino slips silently through the crust of the Earth, unnoticed by trillions of atoms. It may pass through an entire planet, even a star, without collision. And yet, its presence is not meaningless. It is a witness to events that unfolded mere seconds after the Big Bang. These ghostly particles carry the oldest stories, inscribed in energies too faint for light to tell. Cosmology today is as much about such whispers as it is about light. We listen to these whispers not just with telescopes, but with detectors cooled with liquid xenon, with underground tanks of ultra-pure water, with satellites tuned to background radiation that stretches from the birth of time. This radiation, the cosmic microwave background, was once fire, now cooled to a whispering fog. Its pattern, its tiny temperature fluctuations, carry the imprint of primordial sound waves, density ripples that seeded galaxies. The cosmos began not as a quiet dark, but as a roaring furnace of photons and plasma. Light could not travel freely until atoms formed, decoupling matter from radiation. From that moment onward, light bore witness and memory began. The structure of the universe, from clusters of galaxies to empty voids, formed under the pull of gravity on a scaffolding of dark matter. Yet we still do not know what this dark matter is, nor the dark energy that drives expansion. Together, they make up over 95% of the cosmos. What we understand is a sliver, a luminous trace in a vast architecture of mystery. And still, we map. We simulate universes inside computers, each a possible history. We chart baryon acoustic oscillations, lensing effects, redshift surveys. We send probes beyond Pluto, listen for gravitational waves rippling through space-time, and dig through data for signatures that might hint at multiverses or cosmic inflation. In these explorations, the question of origins shifts shape. What came before the Big Bang? Perhaps nothing. Or perhaps everything collapsed into a quantum seed smaller than a proton, dense beyond comprehension, from which expansion sprang not into space, but as space. Some theorists imagine the universe emerging from a quantum fluctuation, a vacuum burp in an eternally inflating meta-universe. Others propose that time itself began at the Big Bang that before has no meaning. In quantum cosmology, The universe might tunnel into existence like a particle through a potential barrier, governed not by cause, but by amplitude. Such models inspire awe, but also humility. They remind us that our intuitions honed in Newton's orchard, refined in Maxwell's fields, stretched in Einstein's relativity are local tools. The cosmos may not conform to them, and yet, in this immense, strange world, we find resonance. The laws of physics are the same in distant galaxies. The constants Planck's, Boltzmann's, the speed of light are unreasonably stable. Why this symmetry, this coherence? Some invoke anthropic principles, perhaps only universes with such properties allow observers to arise. Others seek a deeper theory, a unifying elegance from which the constants must follow. Still others suggest we live in a simulation, a cosmological program run by unknown agents across unimaginable substrates. But whether computation or contingency, string theory or simulated code, the effect is the same, a cosmos that suggests a logic, even if we do not yet grasp it. That logic, whether natural or numinous, is mirrored in our own striving, in the fact that hydrogen, under the right conditions, becomes consciousness, that dust can dream, that atoms arranged in neural nets can ask why. From Babylon to space telescopes, from clay tablets to quarks, we have turned wonder into method. Our myths became measurements, our stories, simulations. Yet at the heart of it remains the same drive to place ourselves in the unfolding order of things. We measure time in billions of years. We speak of horizons and heat death, but we live in moments, in the flash of discovery, in the stillness of knowing we are part of something old, immense, and unfolding. Our minds, fragile and brief, are also vast in reach. We carry within us the memory of stars. And so, cosmology does not end. It circles. Each new insight reframes the old questions. Where are we? What is everything made of? Will it end? Was it ever meant? These are not merely scientific questions. They are existential, ethical, poetic. They shape how we value life, how we face the unknown, how we find meaning. In the end, perhaps the most radical idea is not that the universe is expanding, or that time began, or that reality is made of probabilities, but that in this vast field of forces and fields, there emerged a species capable of caring about it. We are not the center, but we are a witness, and in that, we are significant. The neutrino passes, the stars turn, the universe continues silent, immense, and possibly infinite. But for now, we are here, listening, and wondering.
A photon races across the void, its journey spanning billions of years from a distant star to a telescope on a Chilean mountaintop. Its arrival, a fleeting interaction with a detector, seems ordinary, yet it underscores a cosmic puzzle. Why does the universe permit such moments, where light, matter, and observation align to create meaning? The laws governing this photon electromagnetic forces, gravity, nuclear interactions are tuned with precision, allowing stars to forge carbon, planets to cradle oceans, and minds to ponder their place. This balance, delicate as a spider's thread, sparks questions about life's existence in a cosmos vast and indifferent. Electromagnetic forces bind electrons to nuclei, shaping molecules essential for life. Their strength, measured in laboratories at institutions like CERN, allows protons and neutrons to fuse in stellar cores, producing carbon, the backbone of proteins and DNA. If this force were fractionally stronger, stars would burn too fiercely, collapsing before carbon forms, weaker, and atoms would drift apart, leaving a universe of scattered particles. The strong nuclear force, holding protons and neutrons in atomic nuclei, is equally precise. A slight increase, and only hydrogen would persist, starving stars of heavier elements. A decrease, and hydrogen itself would vanish, erasing the seeds of chemistry. 12 fundamental parameters, from the gravitational constant to the energy density of empty space, govern this cosmic architecture. Gravity, weak enough to let stars shine for billions of years, permits planets to orbit without spiraling inward. the cosmological constant, dictating space's expansion, balances to allow galaxies to form without tearing apart or collapsing. Experiments at the Large Hadron Collider confirm these values, each so finely adjusted that a nudge in any direction would unravel the conditions for life. A universe without stars, or one of pure hydrogen, would silence the possibility of observers. Earth, orbiting a stable star in the Milky Way's quiet arm, seems a cosmic anomaly. Its axial tilt, 23.5 degrees, stabilizes seasons, nurturing ecosystems. Oxygen, 21% of its atmosphere, fuels respiration, a balance maintained by photosynthetic algae in oceans. These conditions, measured by satellites like GOES, suggest a planet tailored for life. Yet the galaxy, with its 100 billion stars, offers countless other worlds. Are Earth's conditions unique, or do they repeat across the cosmos, hidden in distant systems? The odds of this alignment challenge intuition. A single parameter, like the strong nuclear force, shifting by 1% could erase life's potential. Multiplied across 12 parameters, the probability of a life-friendly universe seems vanishingly small. Ancient philosophers, from Aristotle to Ibn Rushd, saw purpose in nature's order. Modern scientists, at observatories like Mauna Kea, grapple with the same question: is this precision a cosmic fluke, or does it hint at intent? The universe, vast and mostly hostile, with its freezing voids and searing stars, seems an unlikely cradle for life. Yet here we stand. This puzzle drives the anthropic principle, a framework born in the 20th century. Its weak form posits that the universe's properties allow life because only such a universe could host observers. At a conference in Cambridge, physicists debate this: if gravity were stronger, stars would collapse before life emerged, and no one would question the cosmos. The principle, a tautology to some, explains why we see a life-friendly universe. We exist only where life is possible. Like a guest at a feast, savoring a cake flavored to their taste, we attend because the conditions suit us. The strong anthropic principle ventures further, suggesting the universe is compelled to foster life, perhaps intelligent life. At institutions like Caltech, researchers explore this idea, noting life's emergence on Earth within a cosmic blink 4 billion years after the Big Bang. Is life a built-in feature, woven into the universe's laws, or is Earth a rare accident? Its biosphere a singular spark in an indifferent void? These questions, unanswered, linger in the data from telescopes scanning exoplanets, seeking worlds where water flows and skies glow blue. A neuron fires in a human brain, a spark of electrical current crossing a synapse. This fleeting act, repeated billions of times, conjures a thought, a question about the stars overhead. Consciousness, the ability to reflect on the cosmos, emerges from such sparks. Yet its nature eludes the probes of science. While the universe's laws, from gravity's gentle tug to the nuclear forge of stars, align to permit life, it is the mind's awareness that observes this harmony, turning raw existence into meaning. Why does a universe, vast and mostly barren, host beings who ponder its design? In laboratories at Stanford, neuroscientists map brain activity, tracing thoughts to neural patterns. Electrodes capture signals as subjects gaze at a starry sky, their minds wrestling with the universe's precision. Yet mapping a thought does not explain why it feels like wonder, or why self-awareness arises at all. The electromagnetic force, binding atoms in neural membranes, is tuned to allow such complexity, but consciousness remains a mystery. Is it merely a byproduct of biology, a fortunate glitch in evolution's code, or something woven into the cosmos's fabric? Some propose the brain as a receiver, not a creator, of awareness. At the University of Tokyo, researchers study neural oscillations, waves of activity resonating like a radio tuned to a signal. If consciousness exists beyond the brain, a universal field perhaps, the fine-tuned laws, electromagnetic and quantum, might channel it. Panpsychism, a theory debated in journals like Consciousness and Cognition, suggests awareness permeates all matter. Electrons in a star's plasma, quarks in a galaxy's core, carry a rudimentary spark of mind, scaled up in human brains to self-reflection. Quantum mechanics, probed at facilities like Fermilab, hints at consciousness' role. Particles, like photons in a double-slit experiment, shift from waves to particles when observed. At Caltech, lasers fire through slits, detectors clicking as light chooses a path. Unobserved, photons spread as waves, forming interference patterns on screens. Watched, they collapse into points, as if aware of scrutiny. This observer effect, first noted in 1927, suggests reality depends on measurement, a process tied to conscious intent in some interpretations. John Archibald Wheeler, at Princeton in the 20th century, pushed this further. His participatory universe posits that observation shapes existence. A photon, leaving a quasar 10 billion years ago, bends around a galaxy's gravity, splitting into two paths. Telescopes, like the James Webb, capture these paths, forming twin images. If detectors merge both streams, the photon behaves as a wave, its past retroactively set. Wheeler argued this act performed today defines the photon's billion-year journey, linking observer to cosmos across eons. This cosmic interplay relies on fine-tuned parameters. The gravitational constant, measured by experiments at the National Institute of Standards and Technology, allows galaxies to warp spacetime, enabling lensing. Without this precision, light's paths would not converge, and observation's power would falter. Consciousness, observing such events, becomes a co-creator, hammering probabilities into reality. At seminars in Oxford, physicists debate, does the universe require minds to manifest? Or is observation a quirk of quantum rules? The brain, a network of 100 billion neurons, mirrors this cosmic scale. Each synapse, governed by electromagnetic forces, fires in patterns studied at MIT, yet no pattern explains the qualia of seeing a star's light, the felt experience of awe. If panpsychism holds, consciousness scales from particles to minds, a universal trait enabled by the strong nuclear force binding atomic nuclei. A universe slightly weaker in this force would lack complex atoms, silencing minds before they formed. Ancient stargazers, from Mesopotamia's ziggurats, saw constellations as divine. Today, at the Atacama Large Millimeter Array, astronomers parse the same sky, seeking exoplanets where minds might arise. The weak anthropic principle, discussed in segment 1, explains why we observe a life-friendly universe. Only here could we exist to ask. But consciousness's role, shaping reality through observation, suggests a deeper link. Is the universe fine-tuned not just for life, but for minds that perceive its order? This question, unanswerable by equations alone, draws philosophers to conferences in Kyoto. If consciousness is universal, the cosmos's vastness, 10 billion light-years across, becomes a canvas for awareness. From human thoughts to the hum of stellar plasma, the fine-tuned laws, allowing carbon's formation in supernovae, set the stage. Without them, no neurons would fire, no telescopes would scan, no questions would rise. The universe, through its observers, seems to reflect on itself, a mirror of mind and matter. A laser pulses through a vacuum chamber, its beam splitting into two paths before striking a screen. At the European Organization for Nuclear Research, physicists adjust detectors, watching as photons leave interference patterns, ripples of light behaving as waves. When a sensor tracks each photon's path, the pattern vanishes, replaced by distinct dots, as if the light knows it's watched. This double-slit experiment, conducted in 1927 and refined in modern labs, reveals a universe where reality shifts under scrutiny, its fine-tuned laws allowing such paradoxes to shape existence. Quantum mechanics, born from Max Planck's work in 1900, governs particles at scales smaller than atoms. Electrons, quarks, photons, each exists in superposition, a blend of possible states until measured. At the University of Heidelberg, experiments fire electrons through slits, their paths a probability cloud until observed. The fine-tuned electromagnetic force, binding these particles, permits such behavior, enabling atoms to form stable molecules. Without this precision, quantum states would collapse prematurely, disrupting life's chemistry. Schrödinger's cat, a thought experiment from 1935, crystallizes this strangeness. A cat, sealed in a box with a radioactive atom, a Geiger counter, and poison, is both alive and dead until observed. At institutes like Perimeter, Theorists model this superposition, noting the universe's laws allow such ambiguity. The strong nuclear force, holding the atom's nucleus, is tuned to permit rare decays, making the cat's fate a quantum gamble. A slight shift in this force would lock particles in fixed states, erasing superposition's role. Observation collapses, superposition, a process studied at the Australian National University. A photon, in a superposition of two paths, becomes definite when measured, its wave function resolving into a single state. This collapse, tied to consciousness in some views, depends on fine-tuned parameters. The Planck constant, governing quantum scales, ensures particles remain in superposition long enough for observation to matter. If larger, quantum effects would vanish. If smaller, reality would blur into chaos, preventing stable matter. John Wheeler's participatory universe, introduced earlier, scales this to the cosmos. At the Very Large Telescope in Chile, astronomers observe light from a quasar, 10 billion light-years distant, bent by a galaxy's gravity into two paths. Detectors, merging these paths, reveal wave-like interference, as if the photon's billion-year journey was undecided until now. The gravitational constant, measured in torsion balance experiments at the University of Washington, allows this lensing, its precision enabling observation to shape past events. Without it, galaxies would not bend light, silencing this cosmic experiment. Wheeler's vision, debated at symposia in Trieste, suggests observers co-create reality. A star's collapse, observed by the Event Horizon Telescope, becomes real through measurement. Its black hole fixed by data, the fine-tuned cosmological constant, driving cosmic expansion, ensures a universe old enough for stars to form and minds to observe. If faster, galaxies would scatter before life emerged. If slower, collapse would preempt observation. This balance, evident in cosmic microwave background data from Planck, frames a universe where measurement matters. Quantum entanglement, probed at the Chinese Academy of Sciences, deepens this. Two particles, linked across light years, share states measuring one fixes the other instantly. In 1982, experiments at the University of Paris confirmed this, defying classical causality. The fine-tuned weak nuclear force, governing particle interactions, allows entanglement, its strength enabling stable quantum links. Without it, particles would decay too fast, breaking these cosmic connections essential for reality's coherence. Ancient observers, charting stars from Mayan pyramids, saw order in the sky, unaware of quantum rules. Today, at the Square Kilometer Array, radio dishes parse distant signals, revealing a universe shaped by observation. The anthropic principle, weak or strong, explains why we see this order. Only a fine-tuned universe hosts minds to measure it. But quantum mechanics suggests more reality state, from a photon's path to a galaxy's birth, hinges on acts of observation, tying the cosmos to its perceivers. The universe's vastness, with 10 billion galaxies, challenges this view. Most regions, like the voids between clusters, lack observers, their states uncollapsed. At Cambridge, cosmologists model these realms, asking if they exist definitively without measurement. The fine-tuned energy density of space, measured by the Dark Energy Survey, allows such voids, yet life's rarity suggests observation is sparse. Does reality in unobserved corners remain a probability cloud, awaiting a mind's gaze? An electron spins in a cloud chamber, its path forking into countless possibilities. At the Kavli Institute in Delft, physicists track such particles, their trajectories a dance of chance governed by quantum rules. Each measurement, pinning the electron to one path, seems to choose a single reality. But what if every path persists, each unfolding in a separate universe? Hugh Everett's many worlds hypothesis, proposed in 1957, suggests the cosmos splits at every quantum event, creating parallel realities where all outcomes play out. This vision reframes the fine-tuning of our universe as one of infinite variations. Everett's idea, debated in journals like Physical Review, posits that the universe never collapses into one state, as in Wheeler's participatory model. A photon, passing through a slit, takes both paths not as a superposition resolved by observation, but as real trajectories in divergent worlds. At the University of Vienna, experiments entangle photons across kilometers, confirming quantum correlations. The fine-tuned electromagnetic force enabling these links ensures particles interact precisely, allowing each world to branch coherently. A slight deviation would scramble these interactions, halting the multiverse's fractal growth. Schrödinger's cat, alive in one reality, dead in another, lives in parallel universes. At the Perimeter Institute, theorists simulate such splits, noting the strong nuclear force's role in stabilizing atomic decays. This force, tuned to permit rare radioactive events, allows the cat's fate to diverge. If stronger, nuclei would lock, freezing quantum possibilities. If weaker, rampant decays would erase stability. The multiverse, a tapestry of branching realities, depends on this precision, each world a variation on the universe's finely balanced laws. Everett's hypothesis, unlike Wheeler's observer-driven cosmos, requires no conscious measurement. At Oxford, cosmologists model a multiverse where every quantum fluctuation, each particle's spin, each star's collapse spawns a new reality. The cosmological constant, measured by the Dark Energy Survey, drives expansion in our world, but in others, it varies, yielding universes that collapse or fly apart. Only in a narrow range, as confirmed by Planck satellite data, do galaxies form, stars ignite, and life emerges. Our universe, one of trillions, is fine-tuned because we inhabit a branch where tuning permits us. This multiverse, infinite in scope, challenges Earth's centrality. At the Keck Observatory, astronomers scan exoplanets, finding worlds where water might pool. In parallel universes, Earth's twins thrive or perish, each with different axial tilts or oxygen levels. The fine-tuned gravitational constant, measured in Cavendish experiments at the University of Tokyo, allows planetary orbits in our world. Elsewhere, gravity's strength shifts, scattering planets or crushing them into stars. The multiverse, a cosmic lottery, produces every configuration, life-friendly or barren. Ancient Chinese astronomers, etching star maps on oracle bones, saw a singular cosmos. Today, at the Large Synoptic Survey Telescope, machines parse billions of stars, hinting at countless unseen worlds. Everett's hypothesis suggests each observation, every telescope's click, splits reality. Observers branching into parallel selves, the weak anthropic principle, framing our existence as a selection effect, gains new depth. We see a fine-tuned universe because, in the multiverse, only such branches host life. No design is needed. Infinite trials ensure some worlds align for minds. Consciousness, navigating this multiverse, raises questions. At the Max Planck Institute, neuroscientists study decision-making, each choice a quantum fork. In one reality, a scientist chooses to observe a star. In another, they turn away. Everett's model, unlike Wheeler's, assigns consciousness to each branch. No collapse required. The fine-tuned Planck constant, governing quantum scales, ensures these forks are stable, allowing minds to persist across realities. Without it, quantum chaos would merge worlds, erasing distinct experiences. The multiverse's scale, infinite and unseen, dwarfs our galaxy's 100 billion stars. At Caltech, simulations model branching universes, some with altered electromagnetic forces where carbon never forms. These barren realities, lacking observers, exist alongside ours, a silent majority. The strong anthropic principle, suggesting life as a cosmic imperative, finds new context. Life arises somewhere, inevitably, in an infinite multiverse. Yet the question lingers, why does our branch, with its precise tuning, host us? Inca stargazers, aligning temples to the Pleiades, saw a purposeful sky. Modern arrays like ALMA probe the same stars, revealing a cosmos of chance and necessity. Everett's multiverse, driven by fine-tuned laws, offers no intent, only endless variation. Each world, from a photon's path to a galaxy's spin, unfolds in parallel, a kaleidoscope of realities where every possibility finds a home. Our universe, one thread in this tapestry, shines with life, its tuning a stroke of cosmic fortune. A breeze sweeps across the Atacama Desert, where giant telescopes stand silently, scanning the heavens for whispers from distant stars. Light from galaxies 10 billion light-years away carries tales of a universe woven from flawless laws, where every pulse of matter and energy harmonizes to sustain existence. These laws, from the dance of subatomic particles to the expansion of boundless space, have allowed life to emerge on a tiny blue planet, where humans gaze upward and ponder their place in the grand tapestry. Humanity, with its curious minds, has followed starlight to unravel the cosmos's nature, from long nights beside Mesopotamia's ziggurats, where priests mapped constellations, to modern laboratories in Geneva, where physicists peel back the secrets of subatomic particles. This journey is a symphony of discovery. The universe, with its exquisitely tuned laws, is not merely a stage where humans play their part, but a mirror reflecting our deepest questions. Where do we come from? And why do we exist to ask? Life, a rare phenomenon in the vast expanse, springs from atoms forged in stellar crucibles. These atoms, linked by forces calibrated with unimaginable precision, formed molecules, cells, and ultimately minds capable of self-awareness. At conferences in Kyoto, philosophers and scientists debate consciousness's nature, wondering if it's a cosmic accident or an integral part of reality. The universe, seemingly built to permit reflection, invites humanity to explore not just physical laws, but the meaning of its own existence. In the flickering light of quantum experiments, reality seems to hinge on observers' presence. In Vienna's laboratories, photons passing through narrow slits reveal a cosmos where possibilities become real only when measured. The laws enabling this wonder, from the Planck constant to gravity, appear designed to sustain a universe where questions can be answered, where light from distant stars can tell its story to listening minds. Humans, with their ability to observe and reflect, become part of the cosmos, not just spectators but co-creators in its narrative. The universe may be one of countless realities, each with distinct laws, where stars burn differently or never form. At supercomputers in Cambridge, simulations paint worlds where the nuclear force is 1% stronger, yielding universes of pure hydrogen, or where space expands too swiftly, preventing galaxies from coalescing. Our universe, with its perfect conditions for life, may be a single branch in an infinite forest of possibilities. Yet in this branch, humans stand, wielding pens and telescopes to rewrite the cosmos' story. From ancient temples in Machu Picchu, where Inca stargazers watched the Southern Cross, to observatories atop Hawaiian volcanoes, where modern astronomers analyze light from pulsars, humans have sought meaning in the stars' arrangement. The universe's laws, tuned to permit life and consciousness, seem to urge humanity beyond its limits, to seek not just scientific answers but connection to something greater. Each photon's glow, each fleeting thought, is part of a cosmos that appears made to be understood, to be experienced. The universe, with 10 billion galaxies spanning 10 billion light-years, is a vast canvas, where Earth is but a speck. Yet in that speck, human minds have built cities, composed poems, and launched spacecraft to the stars. The laws enabling this, from atoms' stability to space's expansion, feel less like chance and more like an invitation. Humans, with their capacity to see the cosmos and see themselves, bear the responsibility to continue this story, to explore not just physics mysteries, but the mysteries of the soul. When starlight from a distant galaxy touches the retina, it sparks a sense of wonder, a wordless question about the origin and purpose of all things. The universe, with its perfect tuning, offers no clear answers, but it provides a space for humans to search, reflect, and dream. From starlit nights beneath Polynesian skies to the glowing laboratories of the 21st century, this journey testifies to a cosmos not just existing, but alive through the eyes that behold it, the minds that question, and the hearts that dare to hope.
What was there before time? If space had a beginning, what was it born from? Can something truly arise from nothing? And if the universe had a first moment, what caused it? Or was it always there? In a fraction of a second, from a point smaller than a subatomic particle, everything, space, time, matter, energy, came into being. One moment there was nothing. The next, there was a universe. Ours. This is not merely a tale of stars and galaxies. It is the greatest mystery science has ever known. How can there be a beginning to everything? And what, if anything, came before it? Everything we understand about our cosmos is rooted in causality, the idea that events unfold because something causes them to happen. From the fusion inside stars to the orbit of planets, we look for processes, for mechanisms, for reasons. But when it comes to the origin of the universe itself, those rules seem to falter. Some physicists, like the late Stephen Hawking, proposed a radical answer. Perhaps there was no before. If space and time are part of the universe, then the beginning of the universe was also the beginning of time. Before that, the concept of before becomes meaningless, like asking what lies north of the North Pole. Or perhaps the Big Bang wasn't the ultimate beginning, but rather the boundary of what we can currently observe. According to the theory of cosmic inflation, our universe experienced a rapid and incomprehensible expansion in its earliest moments, a burst that shaped the structure of all we see. But inflation may not have ended everywhere. Some theories suggest it continues eternally, spawning countless other bubble universes in an endless multiverse. Other scientists imagine something even more cyclical. In the Big Bounce model, our universe is just the latest in a series, expanding, contracting, and rebirthing itself across infinite cosmic epochs. Still others look deeper into the fabric of spacetime. Roger Penrose proposes that at the extremes, when the universe is unimaginably vast or infinitesimally small, time and scale may lose meaning altogether, rendering the birth and death of universes indistinguishable. And beyond that, the mathematical symphony of superstring theory hints that our universe may be just one membrane, or brain, floating in a higher dimensional reality, its creation the result of a collision between dimensions. Each of these ideas offers a different chapter in the story of creation, but none yet offer the final word. So while the origin of our universe remains unsolved, what we know is this: something did happen. 13.8 billion years ago, our universe began. And in seeking to understand it, we are not only searching for the start of space and time, we are also searching for the boundaries of human understanding. The Planck era, the first pulse of cosmic existence. In the pursuit of understanding the origins of our universe, there exists a boundary, an event horizon of knowledge, beyond which lies not darkness, but rather a blinding intensity of energy and uncertainty. This is the Planck era, the first infinitesimal moment after the universe began, a period so brief, so dense, and so energetic that our deepest theories of physics collapse into paradox and mathematical singularity. To traverse the conceptual terrain of the Planck era is to abandon the world as we know it. The constants of nature, distance, time, temperature, mass, all assume values that defy intuitive comprehension. But it is precisely by grappling with these extremes that we approach the roots of reality itself. At first glance, one might imagine the hottest locales in the cosmos to be found within stars. These massive thermonuclear reactors shine through the centuries, powered by the relentless fusion of atomic nuclei at their cores. Temperatures at the heart of our sun, for instance, reach a blistering 15 million degrees Celsius. A journey into such a stellar furnace would obliterate any conventional matter long before reaching the center. Yet even this infernal heat is moderate by cosmic standards. Supernovae, the violent deaths of massive stars, mark a dramatic escalation in thermal energy. In the explosive collapse and rebound of a dying star's core, temperatures can soar to over 100 billion degrees Celsius. This heat is sufficient to forge elements heavier than iron, seeding the universe with the ingredients for life itself. Yet still, this is not the summit of temperature. That distinction belongs, astonishingly, not to the farthest reaches of space, but to a laboratory on Earth. In 2012, deep beneath the Alps near the Swiss-French border, the Large Hadron Collider at CERN achieved a temperature of roughly 5.5 trillion degrees Celsius. This was the result of smashing lead ions together at near-light speeds, creating a microscopic fireball of quark-gluon plasma, primordial state of matter believed to have existed shortly after the birth of the universe. In that fleeting instant, the LHC replicated conditions not seen in 13.8 billion years. And yet, as titanic as that figure may seem, it is only a fragment of the full picture. The maximum temperature that the universe can theoretically support is far beyond what our particle accelerators can touch. This upper bound is known as the Planck temperature, the highest meaningful temperature in physical theory. Beyond this point, temperature ceases to be a useful concept, because the energies involved would tear apart the very particles that constitute reality. Temperature, in the language of physics, is not merely a measure of heat. It is the average kinetic energy of particles, their motion, vibration, and agitation. At absolute zero, all motion theoretically ceases. At the opposite extreme lies the Planck temperature, a figure so immense that it marks the limit beyond which matter and energy can no longer coexist in known forms. It arises from a confluence of constants, the speed of light, the gravitational constant, and Planck's constant, a trio of quantities that together define the Planck units. These natural units set the scale at which quantum mechanics and gravity converge into a single inseparable phenomenon. Max Planck, the pioneering German physicist whose name graces these concepts, introduced the idea of quantized energy at the dawn of the 20th century. His work laid the foundation for quantum theory, beginning with the revolutionary insight that light is not a continuous wave, but is emitted in discrete packets, photons. From this initial quantization of electromagnetic radiation, a new vision of nature emerged, one in which even space, time, and gravity might be subject to quantum rules. From Planck's work arises a set of fundamental units that define the limits of measurable reality. The Planck length, for instance, is the smallest meaningful unit of space, approximately 100 quintillion times smaller than a proton. It is the length scale at which classical ideas of geometry and distance begin to dissolve under the influence of quantum fluctuations. The Planck time, the time it takes for light to traverse a single Planck length, is even more incomprehensible, a fleeting instant, so brief that it makes nanoseconds appear eternal by comparison. This is the age of the universe at the onset of the Planck era, a time when our observable cosmos was only 1 Planck time old and had a diameter of just 1 Planck length. And then there is the Planck temperature. This is not merely the hottest anything can be, it is the point at which traditional physics ceases to be reliable. At this temperature, the energy contained within a single region of space is so concentrated that it distorts space-time itself. Quantum uncertainty and gravitational collapse occur simultaneously, and the very concept of particles breaks down. To understand the relevance of Planck units, one must consider the nature of cosmic expansion. The universe, as we now understand it, has been expanding and cooling since its inception. Whether or not the universe is spatially infinite, it is clear that our observable region, the portion from which light has had time to reach us, is finite, bounded by the age of the cosmos and the speed of light. As we look back in time, the observable universe contracts. Its mass-energy content remains the same, but its volume diminishes. Eventually, we reach the Planck time, the earliest definable moment in cosmic history. At this point, the density and temperature of the universe reach their maximum possible values. The entire observable cosmos, now trillions of times smaller than a proton, is compressed into a fireball of unimaginable energy. This is the Planck era. In today's cosmos, the behavior of matter and energy is governed by four fundamental interactions: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. Each of these forces has a corresponding messenger particle: gluons for the strong force, W and Z bosons for the weak force, photons for electromagnetism, and a hypothetical graviton for gravity. By the end of the 19th century, Planck and others had already begun to see that electromagnetism could be described in terms of quantized fields. Later, it became clear that the strong and weak forces were also susceptible to quantum treatment. Gravity, however, remained the outlier. Einstein's general theory of relativity redefined gravity not as a force, but as the curvature of spacetime caused by mass and energy. This model has withstood a century of experimental verification, from the bending of starlight to the detection of gravitational waves. But it breaks down at quantum scales. During the Planck era, the entire observable universe existed within a volume so minuscule that quantum effects could not be ignored. Gravity, operating on this scale, must itself be quantized. But our current theories cannot describe such a scenario. Herein lies one of the most profound challenges in modern physics: the incompatibility between general relativity and quantum mechanics. Each is supremely successful within its own domain. General relativity governs the large-scale structure of the universe, while quantum mechanics governs the subatomic realm. But at the Planck scale, the two must coexist, and yet their mathematical frameworks conflict. This impasse has spurred the search for a unifying theory: quantum gravity. Such a theory would describe the behavior of gravity in quantum terms, reconciling the smooth geometry of Einstein with the probabilistic fuzziness of quantum physics. Various candidates have emerged. One is the graviton, a hypothetical particle that transmits the gravitational interaction. However, gravity is vastly weaker than the other forces, and detecting a single graviton remains beyond our experimental reach. Other approaches take radically different forms. Loop quantum gravity suggests that space-time itself is not continuous, but composed of discrete loops of quantum geometry. Space becomes quantized, structured, like a woven fabric of microscopic threads. This theory reformulates general relativity in terms of these loops, offering new mathematical tools for addressing gravity on small scales. Perhaps the most ambitious proposal is string theory. String theory also gives rise to M-theory, an overarching framework that includes not just strings, but also higher dimensional objects known as branes. These entities may stretch across multiple dimensions, and their interactions could give rise to entire universes. Even in the absence of experimental data, theoretical physicists have attempted to visualize the texture of space-time at the Planck scale. In the 1950s, the American physicist John Archibald Wheeler introduced the concept of quantum foam, a seething, dynamic structure underlying the fabric of space-time. According to Wheeler, the uncertainty principle renders space and time fundamentally unstable at the smallest scales. Instead of smooth continuity, the Planck-era universe resembles a chaotic froth. Tiny wormholes and micro-black holes flicker into and out of existence, governed by fluctuations that defy classical causality. The orderly space-time we experience today emerges from this quantum chaos only as the universe expands and cools. In such a regime, it becomes impossible to measure position, energy, or time with precision. the very concepts we use to describe physical phenomena lose their coherence. And yet, out of this uncertainty, order will eventually emerge. The Planck era does not last. It is over almost as soon as it begins, 100 million trillion trillionths of a second after the Big Bang. Yet, in that ephemeral flicker, the stage is set for everything that follows. As the universe expands, it cools ever so slightly. The quantum fluctuations begin to stabilize. The fundamental forces differentiate from one another. The first particles condense from energy. This marks the end of the Planck era and the beginning of a universe that, while still unrecognizably alien by modern standards, can be described by the laws of physics we know today. From this moment forward, we can trace the universe's evolution with increasing clarity through the formation of atoms, stars, galaxies, and eventually, life. But the mystery of that first moment remains. It is the question at the heart of cosmology, quantum physics, and gravitation alike. What happens when all the forces of nature become one? The answer remains hidden, encrypted within the mathematics of theories yet to be proven, and perhaps forever beyond the reach of experimentation. Still, to gaze backward into that initial moment is not futile. It is an act of intellectual courage, a tribute to the human spirit's unyielding drive to understand. In contemplating the Planck era, we confront not only the limits of our knowledge, but the birth of reality itself. Grand unification, the first flicker beyond the Planck curtain. In the modern cosmos, all matter and energy conform to the governance of four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These invisible agents dictate the behavior of everything from galaxies to atoms, from the orbit of Earth around the Sun to the biochemical flicker of neurons in a human brain. Yet these forces are not equals. Gravity, despite shaping the architecture of stars and planetary systems, is the weakest among them, so feeble, in fact, that a modest flex of the human arm can overcome Earth's gravitational pull. Contrast this with the strong nuclear force, an overwhelming adhesive that binds protons and neutrons within atomic nuclei and ensures the cohesion of matter itself. Electromagnetism is no less pivotal, enabling light, electricity, chemistry, and the very sensory interaction between our minds and the material world. The weak nuclear force, often overlooked due to its name, plays a vital role in radioactive decay and the nuclear reactions that power the stars. In our present epoch, these forces appear distinct, their identities well-defined, and their behaviors experimentally verified. But the early universe was a far more chaotic and exotic domain, a crucible in which the distinctions we now observe were blurred and the boundaries between forces collapsed. Immediately following the Planck era, during what is known as the Grand Unification Epoch, the cosmos operated under a dramatically reduced set of physical rules. The four fundamental forces were not yet separate. Instead, the universe was governed by only two: gravity and emerged force, uniting the strong, weak, and electromagnetic interactions. To comprehend how three distinct forces could dissolve into one, we must turn to the concept of energy unification. At high enough temperatures and densities, the familiar properties of these forces begin to shift. Analogously, consider a spinning coin in the air. Before it lands, the coin does not present a definite face. The distinction between heads and tails blurs into a whirling unity. Only once its kinetic energy dissipates does the coin settle, and the outcome becomes determined. This metaphor captures the spirit of unification at high energies. As we elevate the temperature, the electromagnetic and weak nuclear forces begin to merge, forming what physicists term the electroweak force. At even higher energy thresholds, far beyond what our current particle accelerators can achieve. The strong nuclear force is predicted to join this union. The result is a theoretical composite interaction known as the electrostrong force. The grand unification epoch is defined by the reign of this unified interaction. Grand unification theories, as proposed within the framework of quantum field theory, strive to mathematically describe this convergence. Although the electroweak unification has been empirically verified through experiments at CERN and other particle colliders, the unification of the strong force remains speculative. The requisite energy scale, around 10 to the 16th GeV, is utterly beyond current human engineering. Not even the cataclysmic energies of supernovae or relativistic jets from black holes approach this threshold. Thus, the electrostrong interaction exists only in theory, a tantalizing glimpse at the possible symmetry of nature's foundation. During the fleeting instant of grand unification, beginning just after the Planck time, the universe was unimaginably hot and dense. Temperatures soared to 10 to the 32 Kelvin, and space-time itself was subject to quantum fluctuations. In this realm, particle identity was not fixed. Instead, the universe seethed with instability and transformation. Particles flickered into and out of existence, mediated by force carriers that themselves defied stable classification. Photons transmuted spontaneously into quark-antiquark pairs. Leptons decayed into hadrons, and all of this occurred in a bath of pure energy, constrained within a spatial volume smaller than a quark. In this bizarre arena, the electrostrong force operated through its hypothetical messengers, unified bosons capable of facilitating transitions not permitted by today's standard model. Quarks could become leptons, and antimatter could transform into matter, and vice versa. Conservation laws, as we understand them now, were not yet enshrined. The universe was fluid, its physical laws still in formation. Symmetry reigned, and identity was optional. But symmetry, as nature so often reveals, is fragile. Roughly 10 to the 36th seconds after the birth of time, a dramatic phase transition shattered this fleeting unity. As the universe expanded, it cooled. The energy density dropped below the unification threshold, and the strong nuclear force decoupled from the electrostrong amalgam. The once spinning coin began to settle. What was one became two, and from this point onward, the strong force operated independently. This symmetry breaking was no quiet affair. It released a tremendous amount of latent energy, seeding the universe with new particles and possibly fueling a period of exponential inflation, an astonishingly rapid expansion that smoothed out the early cosmos and set the stage for the emergence of large-scale structure. Whether this inflationary event coincided precisely with the end of the grand unification epoch remains a topic of theoretical debate, but many models suggest a close relationship. Importantly, this symmetry breaking also introduced a significant problem for physicists: the matter-antimatter asymmetry. Theoretically, the unified force should have produced equal amounts of matter and antimatter, which would have annihilated one another into radiation. Yet our universe clearly favors matter. Every galaxy, star, planet, and person is made from it. The grand unification epoch may hold the key to this mystery. Certain guts allow for processes that violate baryon number conservation, enabling the decay of heavy particles into more matter than antimatter. These so-called baryogenesis mechanisms remain an active area of research, as they could explain why anything solid remains at all. Yet, despite its elegance and promise, grand unification remains experimentally unverified. The energies involved are so immense that we may never reach them in a laboratory setting. Nonetheless, cosmological clues continue to emerge. Instruments like the James Webb Space Telescope, launched in December 2021, are peering deeper into the early universe than ever before, observing galaxies formed just a few hundred million years after the Big Bang. These ancient light signals carry encoded imprints of the physics that shaped the infant universe, and in them, scientists hope to uncover indirect evidence of high-energy phase transitions, inflationary dynamics, or even relics of gut-scale processes such as magnetic monopoles or proton decay. The unification of forces is more than a technical goal of theoretical physics. It is a narrative of return. We seek to trace the path of our complex universe back to its simplest, most symmetric form. Grand unification offers us a vision of the cosmos in its embryonic clarity, when forces had not yet fractured, and complexity had not yet emerged. From this unified primordial field sprang the diversity of phenomena we now observe, from galaxies and stars to atoms and life. Still, a lingering puzzle remains: gravity. Throughout the grand unification epoch, gravity loomed as an outlier. Though present from the first moments of time, gravity was not included in the unification of the other three forces. Its behavior at quantum scales remains unresolved, and theories attempting to bridge this divide, such as string theory and loop quantum gravity, are still speculative. To fully understand the pre-Planckian cosmos, we must solve this final riddle. Only then can we achieve a theory of everything, a complete unification of the four fundamental interactions. Until that day, the grand unification epoch stands as a bridge between the unknowable realm of the Planck era and the more familiar physics that governs our observable universe. It is a fleeting moment in time, a trillionth of a second, yet it represents the profound simplicity from which all complexity descends. In studying it, we not only chase the origins of matter, energy, and force, but also deepen our understanding of the universe's fundamental nature and our place within it. Inflation, the first picosecond of the universe. Among the most dramatic and revolutionary developments in modern cosmology is the theory of inflation, an epoch of exponential expansion hypothesized to have occurred within the first fraction of a second after the birth of the universe. This idea emerged not from philosophical curiosity, but from the pressing necessity to reconcile glaring inconsistencies between observation and theory, and to rescue the classical Big Bang model from internal contradictions. Though the Big Bang framework successfully explains the cosmic microwave background radiation, the expansion of the universe, and the primordial abundances of light elements, it falls short in addressing several profound anomalies observed in the large-scale structure and temperature distribution of the cosmos. The urgency of these issues became particularly vivid with the deployment of the James Webb Space Telescope, situated 1.5 million kilometers from Earth, in a stable orbit around the Sun-Earth L2 Lagrange point. This scientific marvel spent over a year undergoing deployment and calibration before it opened its golden segmented mirrors to the depths of the cosmos. When it finally turned its infrared gaze toward the farthest reaches of the observable universe, the results were startling. In data retrieved from regions corresponding to merely 200 million years after the Big Bang, astronomers discovered galaxies that were not only present far earlier than expected, but were also remarkably structured and mature in their form. This discovery sent ripples through the scientific community, prompting astrophysicist Alison Kirkpatrick to question the very foundations of galaxy formation theory, confessing in a moment of vulnerability that she lay awake at night, wondering if everything she had ever studied had been misguided. The media predictably misinterpreted this introspective moment as an indictment of the entire Big Bang theory. In reality, the discrepancy pointed not to a flawed model of cosmic origin, but to gaps in our understanding of how structures, galaxies, stars, and matter itself emerged so swiftly in the early universe. This mystery is but a fragment of a larger tapestry of problems that plagued the classical cosmological model even before the era of high-resolution telescopes. One of the most striking issues concerns the thermal uniformity of the universe. Despite being filled with localized regions of intense heat, such as the cores of stars and the freezing vacuum of interstellar space, the average temperature of the universe is astonishingly uniform in all directions. Measurements of the cosmic microwave background radiation, a relic glow from the early universe, reveal a temperature of 2.7 Kelvin that deviates by no more than a few microkelvin across the sky. Given that the universe is approximately 93 billion light-years in diameter, and that no light could have traveled between widely separated regions in the time since the Big Bang, this thermal homogeneity poses a serious challenge. It implies that distant parts of the cosmos must have been in thermal contact in the distant past, contradicting the limitations imposed by the speed of light. This conundrum, known as the horizon problem, demands an explanation that allows causal contact between regions that are now far beyond each other's light cones. Compounding this is the issue of cosmic flatness. General relativity dictates that the geometry of the universe is governed by its total energy density. A high-density universe curves positively, closing in upon itself like the surface of a sphere. A low-density universe curves negatively, spreading out like a hyperbolic saddle. Somewhere between these two extremes lies a state of perfect spatial flatness. Observations, particularly of the cosmic microwave background and large-scale structure, indicate that the universe is astonishingly flat to within a margin of error that suggests a fine-tuning beyond plausibility. Any deviation from perfect flatness in the early universe would have magnified exponentially over cosmic time. The precision required for the universe to remain so flat today is akin to balancing a pencil on its tip for billions of years, a statistical improbability that begs for deeper explanation. This dilemma is known as the flatness problem. There is yet another paradox embedded in particle physics. Many grand unified theories, which seek to unify the strong, weak, and electromagnetic forces at extremely high energies, predict the formation of magnetic monopoles, particles possessing a single magnetic pole, either north or south. Unlike electric charges, where isolated positive and negative charges exist in abundance, no such monopoles have ever been observed for magnetism. Every magnetic field we detect is a dipole, with inseparable north and south poles. Theoretically, the early universe should have produced a vast number of magnetic monopoles, but none have been detected. Their absence presents an unresolved inconsistency between theory and observation, one that standard cosmological models fail to address. It was under the weight of these cumulative anomalies that the concept of inflation was born. In December 1979, theoretical physicist Alan Guth proposed a radical hypothesis while contemplating the monopole problem. He suggested that the early universe underwent a brief but stupendously rapid phase of exponential expansion. Rather than a linear, gradual unfolding of space from a singular origin, Guth envisioned a moment when the universe expanded faster than the speed of light, not in violation of relativity, since it was space itself that expanded, not matter traveling through it. During this fleeting moment, lasting less than a trillionth of a second, the universe doubled in size dozens of times, resulting in a net increase in volume so vast that it fundamentally reshaped the structure and appearance of the cosmos. To comprehend the scale of this inflation, consider the exponential nature of doubling. If a piece of paper 1/10 of a millimeter thick were folded in half, it would double in thickness. Repeating this fold exponentially, 2 folds, 4 folds, 8 folds, yields dramatic results. By the 10th fold, the paper is as thick as a hand. By the 30th, it reaches into space. At 42 folds, the paper's height would stretch to the moon, 51 folds to the sun. At 90 folds, the thickness surpasses the span of the Virgo supercluster, 100 million light-years across. This is the metaphorical scale of the inflationary expansion Guth proposed. From a quantum speck to a galactic sea, in less than a heartbeat of cosmic time. Inflation, in its breathtaking scope, solves the problems that plagued early cosmological models. It explains the thermal uniformity we observe not by asserting faster-than-light communication, but by proposing that the observable universe originated from a much smaller region that was once in causal contact and thermal equilibrium. When this compact region underwent inflation, it expanded beyond the bounds of mutual interaction, but retained the uniformity imprinted in its earlier state. In this way, inflation resolves the horizon problem without violating the laws of physics. Similarly, inflation offers a resolution to the flatness problem. By stretching any initial curvature to near zero, it renders the observable universe effectively flat. Just as the surface of a massive sphere appears flat to someone walking on it, so too does the vast, inflated universe appear geometrically neutral on the scales we can observe. What might be a curved higher-dimensional manifold is to us indistinguishable from a flat continuum. And in the case of magnetic monopoles, inflation provides a dilution mechanism. If these exotic particles did exist in the early universe, their density would have been dramatically reduced by the rapid expansion, spreading them so thinly across the cosmos that detecting even one would be statistically improbable. The observable universe may contain only a few such relics, dispersed over such immense volumes that our instruments have yet to encounter them. Underpinning this theoretical edifice is the inflaton field, a hypothetical scalar field responsible for driving inflation. Initially trapped in a metastable high-energy state, the inflaton field exerted a form of negative pressure, causing space to expand exponentially. Eventually, the field decayed into a lower energy state, releasing vast amounts of energy into the universe in a process called reheating. This marked the end of the inflationary epoch and the beginning of a hot radiation-dominated universe. During reheating, the energy stored in the inflaton was converted into a dense plasma of particles, quarks, leptons, and gauge bosons, setting the stage for the evolution of matter and radiation as we understand them. Crucially, quantum fluctuations in the inflaton field were also inflated to cosmic proportions. Originally minute and transient, these irregularities became the seeds for the large-scale structure of the universe. Regions of slightly higher or lower energy density, when magnified by inflation, formed the scaffolding around which galaxies and clusters would coalesce billions of years later. The cosmic web of filaments, voids, and superclusters finds its origin in the ephemeral jitter of quantum fields in a universe that was still younger than a trillionth of a second. With the end of inflation and the decay of the inflaton field, the universe entered the electroweak epoch. This era, lasting until around a trillionth of a second after the Big Bang, was governed by the unified electroweak force and populated by a churning sea of particles and antiparticles. Despite the presence of massless quarks and leptons, the strong nuclear force remained dormant, and gravity, while present, was largely ineffective due to the absence of massive particles. The universe was a roiling, high-energy plasma, but the laws of physics as we know them were beginning to emerge. Yet, the universe was still incomplete. Mass, the key to gravitational clumping and structural formation, had not yet arisen. The particles remained massless and unruly, immune to the long-range influence of gravity. It would take another symmetry-breaking event, the interaction with the Higgs field, to grant particles their inertia and bind them to the gravitational order that would eventually form stars, galaxies, and planets. Thus, in the brief window following the Planck and Grand Unification epochs, the universe underwent its most radical transformation. Inflation not only redefined the scale and structure of the cosmos, but it also laid the foundation for the physical laws that would govern its evolution. The problems that once seemed insurmountable, thermal uniformity, spatial flatness, the absence of monopoles, now appear as natural consequences of a deeper and more dynamic early universe. The inflationary model is now deeply embedded within the theoretical framework of cosmology. While many details remain unresolved, such as the precise identity of the inflaton field, the mechanism that ended inflation, and the full topology of the multiverse it suggests, the theory offers a profound and coherent narrative for the universe's first moments. It reconciles quantum physics with gravitational theory, and it opens the door to the possibility that our observable universe is but one bubble among many in a vast and eternal cosmic landscape. In this vision, the inflationary epoch stands as the moment when chaos yielded to order, when the seed of time was sown into the fertile void of the quantum realm, and when the first whisper of cosmic destiny was carried on an exponential wind. The Higgs field and the emergence of mass, the first billionth of a second. In the vast, unfolding story of the universe, there are epochs marked not by the birth of matter, nor by the shaping of galaxies, but by profound conceptual transformations, moments when nature redefines what is possible. Among these, the first billionth of a second after the Big Bang stands as a cosmological inflection point. It was in this fleeting interval that the cosmos underwent a critical phase transition, one that broke an ancient symmetry and birthed one of the most foundational properties of reality: mass. From the earliest stirrings of philosophical thought to the precision of modern physics, symmetry has held an exalted position in our understanding of the cosmos. We see it in the biological world, the bilateral symmetry of mammals, the radial harmony of echinoderms, the fractal regularity of plants. These forms are not merely aesthetic. They are energetically efficient, algorithmically simple, and evolutionarily advantageous. Nature, it seems, favors symmetry for the same reason mathematicians do. It reduces complexity while maximizing coherence. But the physical universe, too, is deeply symmetric. In the language of theoretical physics, symmetry refers to invariance, when a system remains unchanged under certain transformations. A sphere, for instance, looks the same from every angle. Likewise, physical laws retain their form whether applied in New York or on Alpha Centauri. Such invariances are not trivial curiosities. They underpin conservation laws, dictate particle interactions, and form the backbone of our most profound theories, from quantum electrodynamics to general relativity. Indeed, the early universe was a temple of perfect symmetry. At the highest energies, moments after the Big Bang, the four fundamental forces we know today were unified in a single elegant field. The cosmos was a seething cauldron of energy and possibility, yet balanced, whole, and conceptually pristine. But like all high-energy systems in thermodynamic evolution, this symmetry could not endure. As the universe expanded and cooled, it began to fracture. The symmetries that had once unified all interactions began to break, a process akin to freezing water. The fluid, continuous state giving way to a rigid, anisotropic lattice. These cosmic phase transitions, driven by energy loss and thermodynamic constraint, signaled the emergence of a new reality, one no longer governed by absolute balance, but by broken symmetry and physical diversity. The breaking of symmetry that defined the first billionth of a second was both dramatic and consequential. Following the end of cosmic inflation and the onset of the electroweak epoch, the forces of nature continued to bifurcate. The strong nuclear force had already branched off during the Grand Unification era. What remained was the electroweak force, a hybrid field that governed both electromagnetism and the weak nuclear interaction. Around a trillionth of a second post-Big Bang, this force too began to separate. The universe cooled to a threshold where the unified electro-weak interaction fractured into two distinct components. The electromagnetic force, mediated by the massless photon, and the weak nuclear force, mediated by the massive W and Z bosons. But this split did more than just diversify the interaction schema of the universe. It introduced an entirely new property into existence: inertial mass. This symmetry breaking did not occur passively. It was driven by the emergence of a new kind of field, a field unlike any before. This was the Higgs field, a scalar field theorized to permeate all of spacetime. According to theoretical physicist Peter Higgs and others working in the 1960s, the Higgs field did not merely exist. It shaped existence. When certain particles interacted with it, they acquired mass. Those that passed through it unimpeded, like the photon, remained massless. It was a universal viscosity, invisible and omnipresent, determining the heft of every fundamental entity in the cosmos. The mechanism by which the Higgs field grants mass is profoundly elegant. Imagine a symmetric field, initially resting at a high-energy state, undergoing a spontaneous symmetry breaking as the universe cools. Like a ball rolling from the peak of a hill into one of many possible valleys, the Higgs field settles into a lower energy configuration. This choice of vacuum state breaks the symmetry, and the field begins interacting selectively with other particles. The strength of this interaction determines the mass of each particle, a subtle coupling that defines the architecture of reality. The search for the fundamental particles of matter has long captivated human inquiry. From the indivisible atomos of Democritus to the electrons and protons of the early 20th century, we have continually sought smaller, more elemental pieces of reality. By the 1970s, physicists had assembled a robust theoretical framework, the Standard Model of Particle Physics, that unified all known particles and interactions into a coherent tapestry. At its core, the Standard Model contains 12 fermions, the building blocks of matter, 6 quarks and 6 leptons. These include the up and down quarks that form protons and neutrons, the electron and its neutrino, and heavier, short-lived cousins such as the charm, strange, top, and bottom quarks, along with the muon, tau, and their respective neutrinos. Alongside these are the gauge bosons, the force carriers, photons, gluons, and W and Z bosons. And yet, there was a glaring omission in this grand framework: mass. The Standard Model, as originally formulated, could not explain why the W and Z bosons were so heavy while photons were massless. Nor could it account for the hierarchy of fermion masses, why the top quark outweighs an electron by a factor of over 300,000, or why neutrinos are so light they are barely detectable. These gaps threaten to undermine the entire edifice. The Higgs mechanism provided the missing link. It postulated that a single scalar field, the Higgs field, couples to all particles through interactions proportional to their mass. The heavier the particle, the stronger its interaction with the field. The W and Z bosons, for instance, interact intensely, explaining their considerable mass, while photons do not interact at all, remaining weightless. Electrons, quarks, and other fermions fall somewhere in between. But this theory came with a caveat. The Higgs boson, the quantized excitation of the field, had to exist. and it had to be found. Confirming the Higgs field's existence required a technological leap. To probe energies corresponding to the early universe's conditions, scientists needed colossal machines, particle accelerators that could replicate those ancient moments. The Tevatron at Fermilab and the Large Hadron Collider at CERN became the central battlegrounds for this experimental quest. It was no easy task. The Higgs boson was expected to decay almost instantaneously into other particles, leaving behind a signature buried in the chaotic wreckage of high-energy collisions. Compounding the problem, the Standard Model offered no precise prediction for the Higgs mass, only bounds within which it might be found. It was akin to searching for an invisible needle in a haystack the size of a planet, with only the faintest ripple in the surrounding straw to mark its passage. Nevertheless, in July 2012, the physics community erupted in celebration. After years of data collection and exhaustive analysis, researchers at CERN announced the discovery of a new particle consistent with the long-sought Higgs boson. The missing piece had been found, the Standard Model was vindicated, and more importantly, the Higgs field was confirmed to be real, forever altering our understanding of the early universe. With the Higgs field activated, the cosmic phase transition was complete. The once perfect symmetry of the early universe was now irreversibly fractured, and with this fracture came form, differentiation, and substance. Particles that had floated massless through the pre-Higgs vacuum were now endowed with mass and inertia, becoming susceptible to gravitational influence and capable of forming bound structures. The electroweak force had split into two distinct interactions, mediated by different bosons of vastly different mass. The photon, exempt from Higgs coupling, remained free to travel infinite distances, laying the groundwork for electromagnetism and light. The W and Z bosons, now massively burdened, became short-range messengers of the weak interaction, central to processes such as radioactive decay. Meanwhile, quarks, now massive, began to coalesce under the strong force into hadrons, protons, neutrons, and their exotic cousins. Electrons, too, now bore mass, allowing them to orbit nuclei, setting the stage for the eventual formation of atoms. The primordial soup of quark-gluon plasma, forged in the furnace of inflation and sculpted by the Higgs, now contained all the ingredients necessary for structure. It is worth noting that even with the Higgs field's action, the origin of most mass in the universe is still not the mass of fundamental particles themselves. A proton, for example, derives more than 90% of its mass not from the quarks it contains, but from the kinetic and binding energy of those quarks and gluons within. In other words, the lion's share of mass arises from energy, bound and trapped within quantum systems. Mass is, at its core, a form of confined motion, E equals mc squared given form. By the end of the first billionth of a second, the universe was transformed. The Standard Model particles were in place. The four fundamental forces were separated. The Higgs field had woven mass into the very fabric of the cosmos. The symmetry of the early universe had been beautifully broken, not as a flaw, but as a necessity, a gateway to complexity, to formation, and ultimately to life. The quark era had now begun in earnest. The universe, still unimaginably hot and dense, was dominated by free quarks and gluons, suspended in a high-energy plasma. But as expansion continued, temperatures dropped further. Within microseconds, quarks began to bind into protons and neutrons. Within minutes, the first atomic nuclei would form, and hundreds of thousands of years later, atoms would capture electrons, releasing the first light into a dark cosmos. Yet none of that, no stars, no chemistry, no consciousness, could have occurred without the events set in motion during the first billionth of a second. In that minuscule fraction of time, the universe broke its own symmetry, activated the Higgs field, and permitted mass to exist. Without mass, there is no gravity. Without gravity, no galaxies. Without galaxies, no stars. Without stars, no planets. And without planets, no us. What began as an abstract mathematical solution proposed by a modest physicist in the 1960s became, in time, one of the most profound discoveries in the history of science. The Higgs field is not just a component of theoretical physics. It is the invisible medium through which substance is defined. It is the unseen architecture of material being. And it all happened before the universe had even lived for a billionth of a second. Fine-tuning, protons, neutrons, and the vanishing of antimatter. The first millionth of a second. Within the first millionth of a second following the Big Bang, the universe embarked upon a journey of extraordinary refinement, an unfolding not of chaotic disorder, but of subtle calibration. While this early stage was still governed by staggering temperatures and densities, it already bore the fingerprints of balance, proportion, and, most remarkably, fine-tuning. At first glance, the cosmos in its infancy was violent and frenetic. Yet beneath the turbulence lay a tapestry of exquisite precision, a scaffolding upon which all complexity would one day emerge. As we examine this formative epoch, three major themes converge: the delicate calibration of the physical constants, the formation of composite hadronic particles, protons and neutrons, and the puzzling imbalance between matter and antimatter. Each of these elements, though distinct, is inextricably intertwined in the narrative of how a seemingly chaotic Big Bang culminated in a cosmos capable of forming stars, galaxies, and conscious observers. The universe, despite its staggering diversity, is governed by a set of fixed, immutable quantities known as the fundamental constants of nature. These values underpin all physical laws, yet they appear neither derived nor constrained by deeper principles. The speed of light in a vacuum, Planck's constant, the gravitational constant, and the fine structure constant are among these crucial numbers. They define the strength of forces, the stability of matter, and the evolution of cosmic structure. Crucially, they appear arbitrary, yet their values seem delicately chosen. This is not idle curiosity. The values of these constants directly influence the behavior of all matter and energy. Had the fine structure constant, which determines the strength of the electromagnetic interaction, differed by even a few percent, the formation of stable atoms might have been impossible. A larger value would have tightly bound electrons to nuclei, preventing chemical reactions. A smaller one would have made electron capture too feeble for atomic stability. The same holds for the gravitational constant. Were it stronger, stars would burn rapidly and collapse violently. Were it weaker, matter would remain diffuse, and star formation might never commence. Yet it is not just the strength of the fundamental forces that is finely tuned. It is also the masses of the elementary particles themselves. The masses of the up and down quarks, the electron, and the neutrinos are set at seemingly arbitrary but critical values. Why is the down quark slightly heavier than the up quark? Why does the proton weigh less than the neutron? Even the celebrated Higgs mechanism, which provides a process by which particles acquire mass, does not explain why the values are what they are. The constants are, at present, inputs not outputs of our most successful theories. As the universe cooled below 1 trillion degrees around the millionth of a second mark, it transitioned into a phase in which quarks and gluons, once free and unbound, could finally coalesce into composite particles. This marks the onset of the hadron epoch, the formation of baryons, primarily protons and neutrons, became energetically favorable, and the strong nuclear force, mediated by gluons, forged the first stable nuclear matter. The proton, composed of 2 up quarks and 1 down quark, is a positively charged, stable hadron. The neutron, containing 2 down quarks and 1 up, is electrically neutral. Yet this compositional difference has deep consequences. The up quark carries a fractional electric charge of plus 2/3, while the down quark has minus 1/3. 2 ups and 1 down yield a net charge of plus 1, the proton. 2 downs and an up yield 0, the neutron. But this configuration is not a simple static assembly. The internal structure of protons and neutrons is a dynamic quantum sea, a frothing chaos of virtual particles. Quantum chromodynamics tells us that inside hadrons, valence quarks are constantly accompanied by a shifting menagerie of virtual gluons and transient quark-antiquark pairs. Even charm quarks, much heavier than up or down quarks, can momentarily flicker into existence inside a proton before vanishing. These fluctuations, ephemeral and probabilistic, contribute significantly to the total mass and behavior of the hadron. In fact, over 90% of the proton's mass arises not from the mass of its constituent quarks, but from the dynamic energy of the strong nuclear field that binds them. And yet, for all their complexity, these baryons began to dominate the universe's inventory. The interplay of strong and weak nuclear forces governed their formation and transmutation. The weak force, in particular, allowed for transformations between protons and neutrons via processes such as beta decay. In this way, the early universe maintained a dynamic equilibrium between these 2 building blocks of matter. But as the universe expanded, it cooled further, reducing the energy available for such conversions. Around 1 second after the Big Bang, this process began to freeze out. The ratio of protons to neutrons at that moment was no longer governed by thermodynamic equilibrium, but by the relative masses of the up and down quarks. And here, the fine-tuning of nature re-emerged. Because the neutron is slightly heavier than the proton by a margin of approximately 1.3 MeV, the final freeze-out of the weak force left the universe with a surplus of protons. The heavier neutrons, unless bound into nuclei, would decay into protons, electrons, and antineutrinos. As a result, the emerging baryonic matter of the universe skewed strongly toward protons. This imbalance, subtle though it was, had profound implications. Protons, being positively charged, interact electromagnetically and can bind with electrons to form hydrogen atoms, the foundational building blocks of all chemistry. Neutrons, by contrast, are uncharged and cannot form stable atoms alone, while neutrons do serve essential roles within atomic nuclei, providing the nuclear glue that offsets proton-proton repulsion. The proton is the fundamental unit of atomic identity. A universe in which neutrons had been favored would have been a very different place. In such a cosmos, the stability of hydrogen would have been compromised. Chemistry, based upon the diversity of atomic structures, would be nearly impossible. Without long-lived hydrogen, stars could not form, and the nuclear fusion that creates heavier elements would be absent. The universe, though filled with matter, would have remained chemically barren. Thus, the tiny difference in mass between up and down quarks, a product of some deeper mechanism yet to be uncovered, resulted in a proton-biased universe. It is this proton asymmetry that enabled the synthesis of elements, the ignition of stars, and the eventual emergence of biology and consciousness. And yet, another imbalance was unfolding during this same epoch, one no less critical and no less mysterious: the overwhelming absence of antimatter. According to our best understanding of physics, energy can be converted into matter and antimatter in equal parts. Particle-antiparticle pairs, such as an electron and a positron, or a quark and an antiquark, are expected to be created in perfect symmetry. In the early universe, such pairs would have formed abundantly, only to annihilate shortly thereafter, returning their mass to radiation. Given this perfect symmetry, one would expect a cosmic standoff. Every matter particle destroyed by its antimatter twin, leaving behind a sea of photons, but no surviving matter. But that is not what we observe. The universe we inhabit is overwhelmingly composed of matter. There are stars, planets, and galaxies, but virtually no large-scale domains of antimatter. No gamma-ray annihilation signals are observed between adjacent antimatter galaxies. No positronic halos shimmer at the edges of spiral arms. Even in high-energy astrophysical environments, antimatter remains a rarity. Where did all the antimatter go? Current models suggest that for every 1 billion antimatter particles created in the early universe, there were 1,000,000,001 matter particles. That tiny asymmetry, 1 in a billion, was sufficient to seed all the stars and galaxies we observe today. The rest annihilated into photons during the earliest moments of cosmic history. Seeking the roots of baryon asymmetry, physicists call this the baryon asymmetry problem, and despite decades of investigation, its resolution remains elusive. However, certain experimental clues and theoretical frameworks provide tantalizing suggestions. In the 1950s, physicist Qianxiang Wu conducted experiments that demonstrated parity violation in weak nuclear interactions. More specifically, certain decays exhibited a preference for left-handed particles, a clear sign that symmetry was broken in fundamental interactions. Later studies confirmed that CP symmetry, the combination of charge conjugation and parity, is also violated in certain meson decays. This CP violation introduces a potential mechanism by which matter and antimatter might be treated differently by the laws of physics. It implies that in the dense, high-energy milieu of the early universe, processes may have existed that slightly favored the production of matter over antimatter. Yet the known CP violations within the Standard Model are insufficient to explain the observed asymmetry. As such, physicists hypothesize the existence of additional, undiscovered processes that occurred in the early universe. One promising idea involves the role of right-handed neutrinos, hypothetical particles not currently accounted for in the Standard Model. All neutrinos observed to date are left-handed, while antineutrinos are right-handed. The absence of right-handed neutrinos and left-handed antineutrinos may suggest a deeper asymmetry. Some models propose that in the high-energy conditions of the early universe, heavy right-handed neutrinos decayed preferentially into matter, thus seeding the imbalance. This theory, known as leptogenesis, links the mystery of neutrino mass with the origin of matter. Though elegant, it remains unconfirmed. Experiments at neutrino observatories such as Dune and Hyper-Kamiokande may eventually provide clues. But for now, the origin of the matter-antimatter asymmetry remains one of the greatest unsolved problems in physics. A universe balanced on a razor's edge. By the end of the first millionth of a second, the universe had already undergone profound transformations. It had transitioned from a seething quantum plasma into a cosmos populated by protons, neutrons, and photons. The Higgs field had bestowed mass, the strong force had forged hadrons, the weak force had tipped the balance between particles, and amidst it all, the fine-tuned values of nature's constants had enabled just enough asymmetry to allow structure to form. Had any of these values been different, even slightly, we would not be here to ponder them. A slightly heavier down quark? The neutron becomes favored, hydrogen vanishes, and chemistry fails. A slightly weaker electromagnetic force? Atoms fail to bind. a bit more antimatter, everything annihilates. It is a universe balanced on a razor's edge, calibrated not for simplicity, but for becoming. Neutrinos and primordial black holes, the first second. When we gaze into the most distant reaches of the observable universe, the light that reaches us carries with it the echoes of ancient, dramatic processes that took place billions of years ago. Among the myriad signals embedded in this cosmic light are traces of both the most elusive and the most extreme phenomena the cosmos has to offer: neutrinos and black holes. In particular, the first second after the Big Bang stands as one of the most profound periods in cosmic history, where these two contrasting but equally enigmatic entities began to shape the universe in subtle and far-reaching ways. One is a near-massless particle that almost never interacts with anything, while the other is a gravitational behemoth that consumes all that comes near. Yet both have their roots in the early conditions of our universe. At the 1 second mark, the temperature of the universe had dropped to around 10 billion degrees Celsius. This might sound inconceivably hot by everyday standards, but it represented a substantial cooling from earlier epochs where energies exceeded those of the most powerful particle accelerators by many orders of magnitude. At this stage, the basic building blocks of matter, quarks and leptons, had long since emerged, and hadrons such as protons and neutrons had stabilized into a hot plasma. The Higgs field had already endowed particles with mass. The four fundamental forces, strong nuclear, weak nuclear, electromagnetism, and gravity, had become distinct and were now operating in their current forms, albeit within conditions so energetic that their familiar behaviors were distorted. This first second is pivotal because it marks a boundary between eras of theoretical speculation and eras accessible to observational and experimental physics. For most of what occurred before this time, we rely on mathematical extrapolations, high-energy physics, and theoretical frameworks such as quantum gravity and string theory. But from this point forward, we begin to observe phenomena such as the cosmic neutrino background and gravitational imprints of primordial black holes that are, in principle, detectable and testable. Neutrinos, among the earliest particles to decouple from the rest of the matter-energy soup, emerged as one of the first cosmic messengers. In the hot and dense conditions prior to the 1 second mark, neutrinos collided frequently with electrons and positrons, preventing them from traveling freely. But as the universe expanded and cooled, these interactions weakened. Around 1 second after the Big Bang, the average energy of the surrounding particles had dropped sufficiently to allow neutrinos to decouple from matter. From that moment onward, these ghost-like particles began to stream freely across the cosmos, barely interacting with anything, leaving a subtle yet persistent signature known as the cosmic neutrino background. Although this background has not yet been directly observed, owing to the incredible difficulty of detecting low-energy, non-interacting neutrinos, it is a necessary component of our cosmological models. Its indirect effects have been inferred from patterns in the cosmic microwave background and the distribution of galaxies. If we ever develop the technology to detect the CNUB directly, it would extend our observational reach by nearly 380,000 years, providing a glimpse into a time otherwise invisible to us. Modern neutrino observatories, such as IceCube in Antarctica and Super Kamiokande in Japan, are engineered to detect higher energy neutrinos from distant astrophysical events. These instruments are marvels of engineering, utilizing massive volumes of matter, ice, water, or other dense materials to capture the fleeting signatures of a passing neutrino. By studying the paths of Cherenkov radiation created when neutrinos interact with atomic nuclei, scientists can reconstruct the neutrino's origin, energy, and flavor. These tools have already enabled the birth of neutrino astronomy, allowing researchers to study supernovae, gamma-ray bursts, and even the energetic cores of galaxies. Yet these modern detections pale in comparison to what is needed to observe the relic neutrinos of the early universe. With an estimated number density of just 300 per cubic centimeter and incredibly low energy, detecting the C neutrino would require instruments a billion times more sensitive than Klein ones. Projects such as Ptolemy are taking the first tentative steps in this direction, and future technological breakthroughs may eventually reveal this long silent chorus of the universe's birth. While neutrinos slipped away from the early universe with barely a trace, another entity may have taken a far more dramatic role: primordial black holes. These objects are not the result of stellar collapse, but are instead thought to have formed directly from the high-density fluctuations of the early universe. In the first second after the Big Bang, the energy density of the universe was so extreme that tiny quantum fluctuations, magnified by cosmic inflation, could have created regions of slightly higher than average mass density. If these overdensities were sufficient to overcome internal pressure and the outward momentum of cosmic expansion, they would have collapsed directly into black holes. Stephen Hawking was one of the first to explore this idea in depth. In 1971, he proposed that such primordial black holes could form within the first second of the universe, with sizes ranging from microscopic to many times the mass of our Sun. The exact mass of a PBH would depend on the timing of its formation. The later the black hole formed, the more mass it could gather. This idea provides a possible explanation for the otherwise puzzling existence of supermassive black holes at high redshifts, colossal gravitational entities that already existed when the universe was just a few 100 million years old. Galaxies such as the one hosting TON 618, with its central black hole of over 66 billion solar masses, present a challenge to our understanding of black hole growth. The standard model of stellar collapse and accretion simply doesn't offer enough time to reach such sizes, unless an initial black hole seed, such as a PBH, was already in place. PBHs may also offer insights into dark matter. In certain mass ranges, a population of primordial black holes could account for a significant fraction of the missing matter in the universe. However, observational evidence has thus far ruled out many mass windows. Microlensing surveys, such as those conducted by the Macho and Eros collaborations, have failed to detect the expected lensing effects for certain PBH mass ranges. Nevertheless, there remain gaps, especially in the intermediate and supermassive ranges, where PBHs could still plausibly exist. Some PBHs, especially those of low mass, would have evaporated by now via Hawking radiation. This quantum mechanical process allows black holes to lose mass over time, emitting particles in a thermal spectrum. The smaller the black hole, the faster it radiates until it eventually vanishes in a final burst of energy. If such evaporations occurred in the modern epoch, they could produce detectable gamma-ray bursts. Instruments like the Fermi Gamma-Ray Space Telescope have scanned the skies for such signals, but no unambiguous detections have been made so far. The search for PBHs continues on multiple fronts. Some efforts focus on gravitational waves. Mergers between primordial black holes would produce ripples in spacetime that could be captured by observatories like LIGO and Virgo. Future instruments, such as the Laser Interferometer Space Antenna, will extend our reach to lower frequency gravitational waves, potentially detecting mergers that occurred billions of years ago, if confirmed. Such events would open a new chapter in our understanding of the early universe and the role of gravity in shaping cosmic structure. Neutrinos and PBHs, though radically different in nature, converge on a singular point. They offer windows into the first second of existence. Neutrinos are relics of transparency, slipping away from the opaque universe and carrying with them a record of primordial conditions. PBHs, on the other hand, are the remnants of gravitational collapse, a process that permanently sealed away information behind event horizons. One offers subtlety, the other finality. Together, they bookend a cosmic threshold. The first second was not merely a continuation of prior processes, it was a transition from quantum chaos to thermodynamic evolution, from spontaneous symmetry breaking to observationally accessible structure. It was a time when the energy landscape of the cosmos stabilized, when particles found identity, and when the first messengers, both in form and in absence, departed on their long journey across time and space. In the great cosmic narrative, the first second stands as a prelude rich with consequence. Neutrinos, nearly invisible yet numerous, whisper across the cosmos the story of their origin. Primordial black holes, if they exist, mark the earliest gravitational imprints, frozen scars in spacetime left by quantum tremors. And as we refine our instruments and sharpen our theories, we draw ever closer to reading these signals not as mysteries, but as data, clues left behind in the wake of creation. What lies within that first second is no longer just theoretical territory. It is the emerging frontier of physics and cosmology. And it is in that frontier that the next generation of discoveries awaits, promising to illuminate not only the origins of the universe, but the very principles that govern all its subsequent evolution. Big Bang nucleosynthesis, the first minute. In a secure chamber deep beneath the Lawrence Livermore National Laboratory, a sphere of gold, no larger than a thimble, was blasted by the focused energy of 192 converging laser beams. In less than a fraction of a second, the inside of that golden cylinder reached a temperature hotter than the surface of the sun. Under the weight of that energy, a pellet of hydrogen isotopes, deuterium and tritium, was imploded, squeezed to a density and pressure reminiscent of stellar cores. And for the first time in human history, a self-sustaining fusion reaction occurred in a laboratory that released more energy than it consumed. It was a triumph nearly 7 decades in the making, but nature had mastered this process long ago, not in a lab, nor even in a star, but within the first minute of time itself. Before the first stars blinked into existence, before galaxies began their dance across the expanding void, the newborn universe was already hard at work in its role as an alchemist. In the inferno of its first moments, it forged the elements, hydrogen and helium above all, that would one day become the fuel of stars, the backbone of chemistry, and the substrate for life. And it did so, not in centuries or millennia, but in a window that spanned less than 20 minutes. In the earliest moments, the universe was too hot, too dense, and too violent for anything stable to exist. Quarks, the building blocks of protons and neutrons, swam freely in a quark-gluon plasma, colliding and ricocheting at nearly the speed of light. But as expansion gradually cooled the cosmic soup, these quarks began to bind into the first baryons, protons and neutrons. That process alone was an enormous leap in structural complexity. For the first time, the universe had matter, not merely as fleeting energy fluctuations, but as particles with identity and permanence. Yet forming these hadrons was only the beginning. What mattered next was how they would combine. And it was here that the universe began the delicate process of nucleosynthesis, the creation of atomic nuclei from the raw materials of protons and neutrons. This did not happen instantly, though protons and neutrons were abundant, and the strong nuclear force was capable of binding them together. The early universe was not yet ready. Temperatures were still too high, and the ocean of photons that permeated all of space was too energetic. Whenever two nucleons did manage to form a nucleus, say a deuteron made of one proton and one neutron, it was almost immediately blasted apart by an oncoming photon. The density of high-energy radiation was so overwhelming that for every baryon, there were over 1 billion photons. No matter how often particles fused, they were quickly undone. This period of frustration is known to physicists as the deuterium bottleneck. Deuterium, the isotope of hydrogen with one proton and one neutron, is a necessary intermediary in the formation of helium and other light elements. Without stable deuterium, the synthesis chain could not proceed. And so, for the first 3 minutes of cosmic time, despite the abundance of matter and the strength of the strong force, the creation of heavier nuclei was held back by the sheer energetic chaos of the early universe. But the cosmos was cooling. Second by second, as space expanded, the average temperature dropped. When it finally reached around 1 billion Kelvin, something changed. The photons, though still plentiful, no longer had the energy to consistently photodisintegrate deuterium. The bottleneck broke. Suddenly, deuterium nuclei could survive long enough to participate in further reactions. This small shift, almost imperceptible in the tumult of creation, triggered a chain reaction that altered the fate of the universe. Once stable deuterium existed, the floodgates opened. Deuterium fused with protons to form helium-3, or with other deuterons to form helium-4, which includes 2 protons and 2 neutrons, and is one of the most stable nuclei in the universe. Other pathways created trace amounts of tritium, lithium, and even beryllium. But the window was short. As the universe continued to expand and cool, these reactions became less frequent. Within 20 minutes, a nuclear furnace of the universe sputtered and died. The energy required to sustain fusion reactions dropped below the threshold, and the cosmos moved on. Yet in that brief interval, it accomplished something profound. By the time nucleosynthesis ended, the universe was composed of roughly 75% hydrogen and 25% helium by mass, with tiny traces of deuterium, helium-3, and lithium-7. The rest, carbon, oxygen, nitrogen, iron, and the 90 other naturally occurring elements, would have to wait for the lives and deaths of stars to be born. But the foundation had been laid. The ingredients were present: the fuel for stars, the medium for chemistry, and the seeds for complexity had all been forged. What is remarkable about this process is how well we understand it. Through nuclear physics and thermodynamic modeling, cosmologists can predict with exquisite accuracy the abundances of the light elements. And when these predictions are compared with the observed composition of the oldest stars and the interstellar medium, the match is astonishing. The helium fraction, for instance, remains nearly identical to that calculated from the conditions of the early universe, despite the passage of nearly 14 billion years. This consistency is one of the most compelling confirmations of the Big Bang theory. Yet the success of Big Bang nucleosynthesis is not merely in its predictions, but in the way it reveals the delicacy of the universe's initial conditions. Had the neutron been only slightly heavier relative to the proton, more of them would have decayed before fusion began, resulting in less helium. Had the expansion rate of the universe been marginally different, the fusion window might have opened too early or too late, altering the entire balance of elements. The nuclear binding energies, the strength of the strong and electromagnetic forces, the photon to baryon ratio, all had to fall within narrow bands to permit the creation of a chemically rich universe. It is this fine-tuning that continues to inspire awe among cosmologists. If the density of matter had been even slightly higher, the reactions would have proceeded further, converting too much hydrogen into helium. Without sufficient hydrogen, stars like our Sun would never ignite. On the other hand, if the matter had been too diffuse, then deuterium formation might never have become efficient, and fusion would have stalled before helium emerged. Either way, a universe filled predominantly with inert hydrogen or overabundant helium would likely be sterile, without complex chemistry, without stars, and without observers. As it stands, the balance struck in those first minutes was extraordinary. When stars finally formed hundreds of millions of years later, they inherited this primordial composition. It is from this mixture that stellar fusion continued the cosmic transmutation, forging heavier elements in their cores and scattering them in supernovae. The carbon in our bodies, the calcium in our bones, the iron in our blood, all these came later, but the hydrogen in the water we drink, and much of the helium that gives stars their light, was born in the first breath of time. When researchers at the National Ignition Facility successfully created a net positive fusion reaction in 2022, they were celebrating not just a technological achievement, but a connection to the universe's deepest history. The deuterium and tritium they used, hydrogen isotopes produced in minute quantities on Earth, are the same isotopes formed in the Big Bang, suspended in the cosmic plasma over 13 billion years ago. In their implosion chamber, they echoed on a microscopic scale what the universe had once achieved effortlessly on a grand scale. There is something poetic in the idea that the fusion of two simple nuclei, a proton and a neutron, could be the gateway to everything. From the tiniest combination of matter emerges the potential for stars, for life, and for thought. And it all began not in the heart of a star, but in the first minute after the universe was born. But the end of nucleosynthesis did not mean the end of nuclear potential. Though the cosmic forge had cooled, it left behind a reservoir of energy-rich matter suspended in space, an elemental legacy awaiting the gravitational sculpting of stars. The universe, now composed of simple nuclei and a bath of photons and neutrinos, had begun to resemble the version we observe today in its broadest strokes, even though no stars yet twinkled and no atoms had yet formed. The primordial matter was still a hot, ionized plasma in which electrons had no stable orbits around nuclei. Light was scattered and absorbed constantly, trapped within a fog of charged particles. Transparency, and with it the release of the cosmic microwave background, would not arrive until hundreds of thousands of years later. Still, what occurred in those first few minutes had already determined much of what was to follow. The relative abundances of hydrogen and helium, the survival of deuterium, and the scarcity of lithium and beryllium were locked into place, encoded into the composition of the cosmos. These light elements would become the fuel of the first stars, the scaffolding upon which the next stage of nuclear evolution would build. Without them, the heavy elements forged later in stellar cores and supernovae, the building blocks of planets, oceans, and living beings, could never have come into being. And, remarkably, this entire phase of cosmic history unfolded without the presence of stars, galaxies, or any large-scale structure. Gravity had not yet drawn matter into dense clumps. The universe was still largely homogeneous, a nearly featureless expanse, save for minute quantum fluctuations in density. Seeds that inflation had magnified, and which would eventually become galaxies. But at this early stage, fusion did not require complexity or structure. It only needed temperature, time, and the right ratio of particles. The laws of physics, operating without intervention, carried out the synthesis that defined the material basis of the universe. The end of primordial nucleosynthesis arrived not with a sudden halt, but with a gradual decline in reaction rates as the universe continued to cool and expand. Temperatures fell below the threshold necessary for new nuclear interactions. Deuterium and helium could no longer combine into heavier elements. The densities were too low, the average energies insufficient. Lithium and beryllium, though formed in small quantities, were not produced in significant abundance. And so the nuclear furnace of the cosmos shut down after 20 minutes, leaving behind a universe now defined by persistence rather than change. From this point forward, chemistry would wait for atoms to form. Stars would wait for gravity to collapse matter. But the most fundamental step, the emergence of elements from subatomic chaos, had already occurred. When we look at the sun and see its brilliant fusion reactions, we are witnessing a continuation of a process that began in the earliest epoch of cosmic time. And when we analyze the composition of ancient gas clouds, we are peering back into the elemental DNA of the universe, unchanged since its first breath. Even now, the proportions remain remarkably constant. Observations of the oldest stars and the most pristine regions of interstellar space reveal the same 75 to 25 mass ratio of hydrogen to helium that the equations of Big Bang nucleosynthesis predict. The deuterium abundance, sensitive to the density of ordinary matter in the early universe, matches precisely with our measurements. Lithium, slightly more uncertain, nevertheless, lies within observational constraints. The success of these predictions, made decades before precise measurements were possible, stands as a triumph of theoretical cosmology, a bridge between the mathematics of particle physics and the visible structure of the universe. And perhaps most profoundly, this phase of nucleosynthesis is universal. It occurred everywhere at once. Unlike stellar fusion, which is confined to the hearts of stars and triggered by gravitational collapse, Big Bang nucleosynthesis was cosmological in scale. Every region of the universe experienced it. Every cubic meter of space was a crucible. It is for this reason that the light elements are so uniformly distributed across the cosmos, and why they serve as a fingerprint of the universe's infancy. Wherever we look, whether to ancient stars, to distant galaxies, or to the emptiest voids, we find the same elemental story written in hydrogen and helium. There is an elegant simplicity to this process. From an undifferentiated fireball governed by quantum uncertainty, the universe cooled, stabilized, and set in motion the sequence that would eventually lead to complexity. But in its first minute, it already achieved the transition from raw energy to structured matter. It built, from the most basic ingredients, the stable nuclei that would endure for billions of years. That this happened without intervention, without external guidance, purely through the interaction of forces and particles governed by universal constants, is a testament to the profound power and order inherent in the laws of physics. And so, we return to our laboratories, attempting with lasers and magnetic confinement to replicate what the universe accomplished in its infancy. Every fusion experiment, every probe of high-energy nuclear interactions, is a footnote in a story that began long before Earth existed. When we finally achieved net positive energy from fusion in the lab, we were not discovering something new. We were rediscovering the first triumph of matter, echoing the work the cosmos had already perfected in its first fiery breath. The first molecule, first 100,000 years. Life, in all its complexity and unpredictability, is ultimately a story of chemistry. It is the chemistry of molecules interacting, bonding, and transforming across time and space that underlies every biological function. And though life as we know it has only arisen on a single rocky planet orbiting a modest star in a quiet corner of the Milky Way, its chemical foundations may have been written in the stars long before Earth even existed. Understanding how these molecular foundations formed requires a journey into the deep past of the cosmos, to an age not of biology, nor even of atoms as we know them, but to a universe only 100,000 years old. By this point in time, the initial violence of the Big Bang had long given way to relative calm. The intense nuclear reactions that dominated the first minutes of cosmic time had ended, leaving behind a universe filled with the lightest nuclei, hydrogen, helium, and traces of lithium. But these nuclei were still unbound to electrons, drifting in a sea of hot plasma, their electric charges preventing the formation of atoms, much less molecules. The universe remained a dense and brilliant fog of charged particles and photons, with temperatures far too high for stable atoms to form. And yet, amidst this charged chaos, the seeds of chemistry were being sown. As the cosmos continued to expand and cool, temperatures gradually fell toward a critical threshold. It was only once the average thermal energy of particles dropped below certain ionization potentials that electrons could begin to bind to nuclei, forming the first neutral atoms. Helium, with its uniquely high ionization energy and low reactivity, was the first to capture electrons, forming neutral helium atoms. Hydrogen, despite being more abundant, required a further drop in temperature before it could do the same. But in this narrow window between ionized chaos and atomic calm, a remarkable interaction occurred, the formation of the universe's first molecule. Known as helium hydride, this fragile molecular ion consists of a helium atom bonded to a proton. Though highly unstable and rarely encountered today, helium hydride marks the earliest instance of a chemical bond in the cosmos. Its existence is a testament to the universe's inherent tendency towards structure and complexity, even under the most primitive conditions. Theoretical predictions of helium hydride formation date back decades, with models suggesting that such a molecule could arise in the early universe once neutral helium and residual protons coexisted in sufficient abundance. The process relies on the strong electron affinity of helium ions, which, when immersed in a plasma with hydrogen ions, could steal electrons and form transient bonds. Though short-lived, these interactions paved the way for more complex chemistry to emerge as temperatures dropped further. The direct detection of helium hydride in space, however, proved to be an elusive goal. For many years, astronomers searched for its spectral signature without success. It wasn't until 2019 that researchers aboard the airborne Sophia Observatory, equipped with the Far Infrared Receiver GREAT, finally detected the molecule within the planetary nebula NGC 7027. This environment, with its hot, ionized gas and abundant ultraviolet radiation, mirrored in many ways the conditions of the early universe. The discovery confirmed that helium hydride could indeed form under natural cosmic conditions, validating decades of theoretical work and reinforcing our understanding of primordial chemistry. But while the molecule observed in NGC 7027 is not itself primordial, its formation mechanism strongly supports the idea that helium hydride would have been the universe's first molecule. The early cosmos, though lacking stars and planets, was replete with the ingredients and conditions necessary for such a bond to emerge. Once helium hydride appeared, it opened the door to additional molecular interactions. It could react with other protons, potentially leading to the formation of molecular hydrogen ions, and eventually to neutral hydrogen molecules as cooling continued. These simple reactions marked the beginning of a chemical evolution that would stretch across billions of years. Today, the field of astrochemistry reveals that the universe is far more chemically active than once believed. From clouds of interstellar gas to the icy shells of comets, complex organic molecules have been found in abundance. Aldehydes, alcohols, nitriles, and even amino acids have been detected in meteorites and interstellar space. These findings suggest that the precursors of life's essential molecules may not have formed exclusively on Earth, but may have been seeded across space, delivered by comets, asteroids, or even interstellar dust. Supporting this notion are the discoveries made in meteorites such as the Murchison meteorite in Australia and the Tagish Lake meteorite in Canada. These space rocks contain not only amino acids, but also nucleobases, the very building blocks of DNA and RNA. The presence of these molecules in extraterrestrial material strongly indicates that complex organic chemistry was taking place long before Earth coalesced into a planet. The origins of life, therefore, may lie not in a terrestrial primordial soup, but in a broader cosmic context. Yet it is essential to remember that the first step in this long chemical journey was the formation of the simplest possible molecule, helium hydride. Its creation marked the moment the universe shifted from a state of pure nuclear physics to one in which chemistry could take hold. Though it was a fleeting and unstable entity, helium hydride demonstrated that the universe was capable of forming bonds, of creating structure, of moving beyond chaos. From that point onward, as cooling continued, electrons settled into stable orbits around nuclei. Atoms became abundant, and more complex molecules formed. Eventually, gravity gathered these atoms into stars, and within their hearts, fusion created heavier elements. The periodic table, once confined to 3 or 4 elements, expanded. Planetary systems emerged. Water condensed. Organic molecules assembled. And somewhere, perhaps on Earth alone, or perhaps on countless worlds across the galaxy, those molecules began to organize, to replicate, and to awaken. The first molecule of the universe was not part of life. It did not swim in a cell or replicate like DNA. But it was a beginning, a quiet, momentary link in a vast chain of becoming. And in its ephemeral existence, it whispered the first lines of the chemical language that billions of years later would become the poetry of life itself. First atoms, first light, first 380,000 years. The universe, in its infancy, was not the placid tapestry of stars and galaxies we observe today. It was a seething ocean of energy, chaos incarnate, filled with a fog of blinding light and cascading particles in collision. For hundreds of thousands of years after the Big Bang, the cosmos remained opaque, not for lack of light, but for the inability of light to escape the furious interplay of matter and radiation. This was a time when photons, the very carriers of electromagnetic energy, found themselves trapped in an endless labyrinth of charged particles, bouncing incessantly off free electrons and protons, unable to travel more than a hair's breadth before being scattered again. Reason for this entrapment lay in the fundamental properties of matter and radiation at high energies. In those early epochs, temperatures soared above several thousand Kelvin. At such energies, atoms could not exist. Any attempt by a nucleus to capture an electron was immediately undone by the surrounding photons, which possessed more than enough energy to knock the electron away. The universe existed in a state of plasma, a hot, dense mix of free protons, electrons, helium nuclei, and radiation, all mingling in a turbulent sea. It was, in essence, a cosmos in gestation, awaiting the conditions necessary for atomic structure, stability, and transparency. The birth of the first atoms was not instantaneous, but gradually, driven by the relentless expansion and cooling of space. Over the course of 380,000 years, the universe's average temperature fell to around 3,000 Kelvin. At this critical threshold, the balance shifted. Photons no longer had the energy to consistently strip electrons from their nuclei. For the first time, the electromagnetic force prevailed. Electrons spiraled inward and became bound to hydrogen and helium nuclei, forming the first stable atoms. The plasma recombined into a neutral gas, and with that, the universe underwent one of its most dramatic transitions. With free electrons now bound within atoms, the primary obstacles to photon travel vanished. Light was free to stream across space, unimpeded, for the first time in cosmic history. This moment, known as recombination, marked the transition from a universe filled with a blinding, scattering mist to one that was suddenly transparent. The light released at that moment continues to travel through the cosmos to this day. Redshifted by the stretching of space over billions of years, it forms what we now detect as the cosmic microwave background, the oldest light in the universe, and the earliest image of the cosmos we can observe. The physics of this epoch is both elegant and complex. The formation of neutral hydrogen and helium atoms involved a delicate interplay of thermodynamics, quantum electrodynamics, and the expansion of space itself. As temperatures dropped, electrons were captured into quantized orbits around nuclei, emitting photons in the process. These photons, too low in energy to reionize other atoms, accumulated as a relic radiation field. The process was statistically governed by the Saha equation, and later, by the more precise Peebles model, which accounted for the finite rates of recombination and the density of the universe at the time. The release of the CMB was not merely a byproduct of recombination, but a cosmic revelation. It encoded in its slight anisotropies the primordial density fluctuations seeded during inflation. These tiny temperature differences, measured to be on the order of a few parts in 100,000, are the fingerprints of quantum perturbations inflated to macroscopic scales. Denser regions held slightly more matter, and over time, gravity amplified these overdensities, drawing in more mass and setting the stage for the formation of stars, galaxies, and the large-scale structure of the universe. The detection of the CMB stands among the most important empirical validations of the Big Bang model. In 1965, Arno Penzias and Robert Wilson, using a repurposed radio antenna in New Jersey, stumbled upon a persistent background hiss that pervaded the sky. After painstakingly eliminating every possible terrestrial source of the noise, including, famously, cleaning pigeon droppings from the antenna, they concluded that the signal was isotropic and universal. Unbeknownst to them, a team at Princeton University, led by Robert Dicke, had been preparing an experiment to detect precisely that signal, the thermal remnant of the universe's first light. Penzias and Wilson had found it first. Their discovery earned them the Nobel Prize and cemented the CMB as a pillar of observational cosmology. In the decades since, increasingly sophisticated instruments have mapped the CMB with stunning precision. NASA's COBE satellite first detected its anisotropies. The WMAP mission refined the resolution, revealing finer structures, and the ESA's Planck Observatory delivered the most detailed map to date, uncovering the minute temperature fluctuations that encode information about the universe's composition, curvature, and expansion history. These maps show a sky modeled with cold and hot spots, each corresponding to regions of slight over and under density in the early universe. But the story does not end with light. The primordial plasma before recombination was not only a medium for radiation, but also for sound. Pressure waves rippled through the dense photon-baryon fluid, driven by the tug-of-war between gravitational collapse and radiation pressure. These oscillations, known as baryon acoustic oscillations, traveled outward from initial density peaks like ripples on a pond. When recombination occurred, the medium changed. Photons decoupled and streamed freely, while baryonic matter was left behind, frozen in place at the wave fronts of these oscillations. The result was a preferred scale in the distribution of matter, a spherical shell of enhanced density that would later seed galaxy formation. Today, the imprint of BAOs can be seen not only in the CMB, but also in the large-scale clustering of galaxies. The characteristic scale, about 150 megaparsecs, acts as a cosmological standard ruler. By measuring this scale at different redshifts, astronomers can trace the expansion history of the universe, constrain dark energy models, and test the foundations of general relativity on cosmic scales. The first atoms and the first light gave the universe visibility, but they also gave it structure. Without recombination, there would be no CMB to observe, and no window into the state of the cosmos at that critical moment. Without atoms, there would be no chemistry, no stars, and no life. The transparency that emerged 380,000 years after the Big Bang did more than release light. It released the potential for observation, for complexity, and for the cosmos to begin writing the next chapter in its story. Even now, more than 13 billion years later, the light from recombination continues to permeate space. It is all around us, omnipresent and enduring, forming a backdrop to every observation we make. Its near uniformity is a reminder of the universe's common origin, while its subtle variations are a map of all that was to come. Every star, every galaxy, every atom in our bodies was born of the structures encoded in that first light. To study it is to peer not just into the past, but into the blueprint of reality itself. Thus, the era of recombination, though brief in the grand sweep of cosmic time, remains one of the most pivotal transitions in the history of the universe. It marked the moment when the cosmos emerged from its veil, when radiation ceased to dominate matter, and when the universe, having taken its first breath, opened its eyes to the light. Dark matter and dark energy, first million years. In the grand narrative of cosmic evolution, the first million years after the Big Bang may appear uneventful compared to the explosive birth of particles and the sudden emergence of light. And yet, it was during this seemingly quiet chapter in the history of the universe that some of the most mysterious and consequential agents of cosmic structure began to assert their influence. These agents, dark matter and dark energy, are invisible, intangible, and yet profoundly influential. Though we cannot see them directly, the fingerprints they leave upon the universe are unmistakable. After the release of the cosmic microwave background radiation, approximately 380,000 years post-Big Bang, the universe entered an era of darkness. Photons, no longer scattered by free electrons, could finally traverse the cosmos freely. But the universe had yet to produce a single star. It was an age of neutrality, filled with primordial hydrogen and helium atoms drifting silently in a vast and expanding sea of cooling space. But this serenity was deceptive. The seeds of structure were already in place. Gravitational imprints laid down by fluctuations in the early universe, amplified by an unseen force, dark matter. The evidence for dark matter's existence stretches back nearly a century to when Swiss astronomer Fritz Zwicky observed an oddity in the Coma cluster of galaxies. The galaxies were orbiting each other at velocities that defied the gravitational pull expected from their visible mass. Zwicky proposed that there must be some form of dunkle materie, dark matter, providing the extra gravitational glue. Though his suggestion was initially met with skepticism, further observations in the latter half of the 20th century solidified the case. Most famously, in the 1970s, Vera Rubin studied the rotational curves of spiral galaxies and found that stars on the outskirts were rotating just as quickly as those near the center, a phenomenon inexplicable without the presence of additional unseen mass. What is remarkable is that dark matter began shaping the universe long before galaxies even existed. In the aftermath of recombination, normal baryonic matter was too hot and diffuse to collapse under its own gravity. However, dark matter, unencumbered by interactions with radiation, began to clump together far earlier. It laid down the invisible scaffolding for the universe, forming dense knots and vast filaments that would guide the collapse of gas clouds into the first stars and galaxies. Baryonic matter fell into these gravitational wells, forming luminous structures in the shadows of their dark matter halos. Though we know dark matter dominates the mass budget of the universe, outweighing ordinary matter by a ratio of about 6 to 1, its precise nature remains elusive. Several hypotheses have been proposed. One posits that dark matter is composed of machos, black holes, neutron stars, or brown dwarfs that simply emit too little light to be seen. Another, more widely accepted theory is that dark matter consists of WIMPs, hypothetical particles that interact via gravity and possibly the weak nuclear force, but not with electromagnetism. Despite intense searches in particle accelerators and deep underground detectors, WIMPs have yet to be observed. Whether dark matter is baryonic or non-baryonic, its role in the formation of structure is undisputed. By the time the universe was 1 million years old, dark matter had already shaped the distribution of matter on the largest scales. It dictated where galaxies would form, which regions would become voids, and how the intricate cosmic web would evolve. In simulations, when dark matter is included alongside ordinary matter, the resulting universe closely resembles the one we see through our telescopes. Without it, the universe would be smoother, dimmer, and far less hospitable to complexity. Yet, dark matter is only part of the story. The other unseen force that governs the fate of the cosmos emerged much later, but is no less important: dark energy. This mysterious component of the universe, which currently accounts for roughly 68% of its total energy density, was discovered only in the late 1990s. At that time, teams of astronomers studying distant Type 1a supernovae, used as standard candles due to their predictable brightness, noticed something unexpected. The supernovae appeared dimmer than they should have, implying they were farther away than expected. The universe, it seemed, was not just expanding, but accelerating in its expansion. This discovery shook the foundations of cosmology. It suggested that a repulsive force, counteracting gravity on the largest scales, was dominating the dynamics of the universe. Dubbed dark energy, this phenomenon is now understood as the primary driver of the universe's accelerated expansion. Its origin, however, remains one of the deepest mysteries in physics. Several models have been proposed to explain dark energy. One of the simplest is the cosmological constant, a term Einstein originally introduced into his equations of general relativity to achieve a static universe, though he later discarded it, believing it to be a mistake. The cosmological constant has returned with renewed relevance. It represents a constant energy density filling space uniformly, a kind of vacuum energy inherent to space itself. Another possibility is quintessence, a dynamic field that evolves over time and could change the rate of cosmic acceleration. Unlike the cosmological constant, which is fixed, quintessence could vary in strength and interact differently with matter and radiation. However, there is currently no experimental evidence to support this model. and the nature of dark energy remains speculative. Despite our lack of understanding, the effects of dark energy are observable. It stretches the fabric of space-time, causing galaxies to recede from one another at increasing speeds. This expansion alters the appearance of large-scale structures and affects the growth of cosmic formations over billions of years. The balance between dark matter and dark energy ultimately determines the fate of the universe, whether it will expand forever, slow to a halt, or collapse in a big crunch. Current data suggest we are headed toward an eternal expansion, a future in which galaxies move beyond each other's observable horizons and the night sky gradually fades to black. In this context, the first million years of the universe represent not just a transition from opacity to clarity, but from potential to structure. The interplay between dark matter and baryonic matter set the stage for everything that followed. From the formation of the first stars to the emergence of galaxies, planets, and life. Dark energy, though still dormant in that early epoch, would later rise to dominate the universe's destiny. We live in a universe composed primarily of things we do not understand. Ordinary matter, the atoms that make up stars, planets, and people, accounts for less than 5% of the total. The rest is dark matter and dark energy, invisible yet essential. These components govern the shape and fate of the cosmos, guiding its evolution from the moment it became transparent to the light that still echoes through the CMB. To uncover their nature is to illuminate the dark scaffolding of reality itself. As our instruments grow more sensitive and our theories more refined, we inch closer to unveiling the secrets that shaped the universe in its infancy. The first million years were not an interlude, but a foundation. In that dark silence, the universe prepared its canvas, and in the unseen, it defined the visible.